All right. Welcome. Welcome to class. This is the last class that I am talking in. So you all get to teach the next class, remember? You get exactly 10 minutes because what was it? It was something like 180 divided by 19 is exactly 10, right? We all remember that? And we didn't check that 180 divided by 19 is 10. We believe it in our hearts, right? And it's very simple, right? We just use one off by one error and we get the exact answer we want. Um, Today is a weird day, and it is weird in the following way. I feel like I have to teach you some deep learning. And I felt like I had to teach you everything up to k-means, and then I felt like I had to give you a presentation day. So I was just gonna like do different deep learning stuff for like 4 hours. And there's pros and cons to this method, right? So I don't think, and well, it's probably no longer true that no one understands deep learning, but for years, no one understood deep learning, right? I suspect the first people that understand it now do exist, right? And probably those are the people that like the very first person that got deep learning to work taught that person in an undergraduate program, and then that person happened to go to a graduate program where there was like also a deep learning program. So there's probably like 4 people that understand. I have a way I'm planning on describing it, but there's one thing that I think is really, really important about deep learning, and it is not necessarily like it is related to what deep learning is, right? But like the reason machine learning, deep learning, AI, and data science are popular is not just because you can multiply 2 matrices together, which you could have done for many, many years. The reason deep learning is popular is because in 2014, some grad student at the University of Toronto rewrote their computer vision framework to run on graphics processing units instead of central processing. So graphics processing units, for those of you that don't know that, that's what you use to mine Bitcoin and play video games, right? So those aren't like real computers. Those are like fake computers for nerds, right? CPUs are what you use to run Excel and Windows and Microsoft Teams, right? So, wow, that's loud. I'm going to go close the, or, okay, there you go. So I have a new computer. I like sent out a bunch of emails and asked nicely. I got a new laptop. Some of you heard me talking about this, and it has an NVIDIA GPU in it. And the NVIDIA GPU is the one that is compatible with graphics processing unit acceleration of deep learning workloads. Now, at home, I also have an NVIDIA GPU in a desktop computer, and I got GPU acceleration to work on that. And it was weird and confusing. So I was going to attempt to live set up NVIDIA GPU PyTorch acceleration in front of you today. Not in the hopes that you will be able to do the same thing, because I expect it to be different on all of your systems, but in the hopes that you can see one person's setup ever, and I just happen coincidentally to talk about enough things that you understand what's going on. So there's the numerical methods, there's the mathematics that forms the deep learning part, but the only reason it's culturally relevant is because of the hardware acceleration. So I'm going to try and show you what the hardware acceleration looks like. And then there's one other thing that I kind of want to talk about a little bit, which is, to me, it was non-obvious how a neural network and a matrix or a data frame were the same thing. And I was planning on just pulling up one of these screens and then writing on the board for like a couple minutes and explaining that if it seems confusing to us. I think if I do all of those things at the same time, you'll understand deep learning about as well as like any normal human, right? And then you can go into the summer and you will probably explore deep learning in more depth in Python for data science if you take that, or not. But at least you will not finish a machine learning class not having heard of deep learning. Now, I I spent a gratuitous number of hours trying to get this stuff to work in R and Python, and to a certain degree, I have done that. I don't have them working in R and Python at the same time or in the same device. So there are snippets of R code that worked at various points in time. There's snippets of Python code that worked at various points in time. And we're going to just kind of have to talk through them a little bit. Having said that, let's get started. I'm going to start to build out the sort of sketch we're going to go through today. So I'm starting on my personal homepage again, but we're not just going to stay here. We're going to go to a few other places. I have two searches pulled up, and I am using Google Search for this, which is reasonable because we're going to use AI acceleration tools developed by Google. So it is reasonable to use specifically Google Search Engine today. Teaching, ML, deep learning. I'm going to also download the QMD. There it is. I already downloaded it once. I'm downloading it again. Deep learning. Okay. I'm going to show one other thing. These slides today are built from a Quarto Markdown document the same way everything else was built from. It is more common in my impression, specifically in the context of two different things, deep learning and Python, to use a .ipymb file that is an interactive Python notebook file. I also have one of those, and I have it connected to something that you don't have to have Python installed locally to use. So I'm going to find that. Oh dear, okay. Does it work? Okay. I'm navigating to my GitHub repository. I'm going to Data 505, and I have added a folder called .ipynb. I didn't see a compelling reason to link this from the website because you kind of already are going to have to be mucking about on the internet in order to get anything to work today. So we're going to go here. This has two things in it. Some of you following along in Discord are aware of the GPU CUDA acceleration notebook that I shared with some of you. That is here. And this is a minimal example of sort of getting GPU CUDA to work at all. You are welcome to look at this and check this out today. This is based on the C programming language, and so it is probably not well suited for data science applications for that reason. The NVIDIA CEO recently gave a talk at GTC, which is their big conference. Does anyone know what GTC stands for? Are any of you NVIDIA fans? It is the... I don't know what it is. Anyways, this thing just happened. They're basically telling people not to use low-level languages anymore and use Python for everything, is the takeaway from this conference. Okay. This is deeplearn.ipynb. This interactive Python notebook file is equivalent to the .qmd file, but it is in a different format. It is in the IPython notebook format. Why am I using that? Well, the interactive Python notebook format is compatible with Google Colab. So I can click this button here. Now I'm going to take this and I'm going to copy paste this link into the Discord. You may want to follow along on this rather than some other device today. Let's go into Discord. Okay. I'm going to open this up into this says Colab, but it's going to open in colab.research.google.com, I think. I'm going to press that button, and you can kind of see the URL popping up at the bottom. This is what Google Colab looks like, and this is what I recommend you use if you are learning something and don't want to install a large amount of muck on your computer. I do not recommend running machine learning workloads on here because it is too slow, because you are using the free version of something, okay? So this is a good way to explore things, which is what we were doing today. Now, I believe if you attempt to run on all of this, it will break. And it will break very specifically because I'm trying to use both the Python and R version of Torch at the same time, and that is ludicrously hard to set up. But you have this now, and you can probably delete cells that don't work and get all the way through class today using this thing. So this is what I've given to you. Now, many of these libraries you already know from various reasons. Pandas is the Python data frames that are equivalent to R. NumPy is something that implements the arrays used in pandas. Matplotlib and Seaborn are the two visualization technologies. sklearn is basically equivalent to Caret. And these top four torch things, that's all the GPU accelerated things. So that's actually what we're going to teach today. Okay. So I have this up. We'll use this from time to time. I'm going to run this right now because I don't know how slow it's going to take in the background. This was not authored by Google. That's okay. It's authored by me. You can definitely trust me 100%. I've never lied to you. I've never lied to anyone. I don't even know what a lie is. Inside of me are two wolves. They both only tell the truth. And they also always contradict each other, which is somewhat surprising. How's everyone doing today? Y'all locked in? Yeah. Ooh, yes. Okay, there's someone's clapping next to someone shaking their head no. You're clapping. Shout out you. I will update the favorite student rankings in accordance with this. They're really in flux this time of turn, right? Like lots of rapid movements. Look at that, by golly, it only took 17 seconds to load all of that stuff. Okay. I believe uniquely of the slides presented this term, these slides were authored solely by Hendrik and then updated by me. These slides do not have Jameson involvement, and you will notice probably the biggest change is, well, there's two big changes. We did switch to Python because we felt like we had to. And then we also switched off of the Wine dataset. So we're going to be just using built-in Python datasets. The purpose of class today is not to use Python. The purpose of class today is to teach you something and then show examples of it in Python and let you deal with the Python either never or in a successive term if you want to. So if you see a language feature you do not understand, you are welcome to ask me about it, or you are welcome to not care about it. Both of those things are legal. Okay? All right. This is all of the imports that I talked through previously. Oh, this doesn't have announcements in it. Model 2, due today, right now. Model 3, due next time. Do you all know how to show a presentation on GitHub Pages, or do you need an example of that? An example would be great. Cool. Okay. Is it warm in here? Does anyone know what to do about that? We're going to cry? All right. Do we want to open a door? Is it colder outside than inside? Okay. So we should prop 2 doors open? Can I get like a show of hands for propping doors open? Is it going to be loud out there? Okay, let's prop some doors open with like chairs. Is it weirder if I do it, or is it weirder if you do it? There's a door there? Okay. So. Oh my gosh, I closed a door on my head the other day, and like this, the back of this. Well, I was like closing the door, but my head was where the door was going, right? More properly, I slammed a door on my head. Yeah. No, no, no. Yeah. Anyways, it really hurt. Okay. Probably. Yeah. I mean, there's a clean break in between. So memory is an imperfect storage medium, right? So I can't necessarily recall who I used it, right? So I have no conception of what I have lost, right? But can something be beautiful if it's not transient, right? So my consciousness is beautiful for that reason. It's like a fickle stream, right? So I have navigated to https://github.com, as should you. And I'm going to press a button that says new. Why am I going to do that? I'm going to create a new repository because that it's easier to all have the same baseline. If you would like to follow along, you're encouraged to do that. Okay? I'm going to press that button. Now, I am not going to base this on any templates or anything, but I am going to do some configuration. I suspect you do not have a lot of options for who the owner is. I am attached to a few organizations. I suspect many of you are attached to no organizations. So, to keep this consistent, I'm going to select the first thing that's just my GitHub username. Okay? CD public. There's also a CD private. No, you're not allowed to know about it. That's why it's called private, right? It has all the answer keys in it. That's where I keep them, right? So every time I check this in, I'm like, oh, that's what the students can see, right? So that's why it's called CD public, right? So I'm going to click that. I'm going to create a repository name. Now, for you all, you're probably going to call this maybe group name final or something like that. But I have this proto markdown thing called final present.qmd, and I will be using that. So I'm going to do demo final. Now, the names of repositories by convention are things that could be names of folders. What is an example of a folder on my device? I'm using Microsoft Windows, so I have a folder called Documents, right? If I were using Ubuntu Linux, I would have a folder called Home. And if I were using Mac OS, I don't know what you have. Does that anyone use Mac OS? Anyone at all? No one? Okay, all right. Put your hands down. Okay, I saw that. I think it's also called Home on Mac OS, right? What are some things that good? What do I mean by good? I mean easy to use. Good folders often have the attribute of not containing capital letters or spaces, which might be unstable on different environments, right? So I'm using an underscore instead of a space. On Microsoft Windows, I have a folder called My Documents with a space. It is very hard to use, right? So I use an underscore instead. And I also prefer to not rely on case sensitivity, so I'm only using lowercase letters. You don't have to do these, but I'm recommending you make these design decisions. This is going to show up in a URL, so a website address somewhere as well. And the website addresses and the file names on your local device are going to be quite similar. They're going to be related. I'm going to add a helpful description, which I mostly do for myself. And it is going to say, this repository. Why am I calling it a repository? That is the name of this thing, right? When we put files on GitHub, and they are managed by a specific group, and they have a specific name, we call that a repository. Repositories can contain files. They're very similar to folders, right? This repository was created in class in Data 505. What is the date? Is it 417? 414? Okay. As an example, for a Data 505 final project presentation. Okay. I'm going to leave this public. Why am I going to leave it public? The point of this presentation is to have something that is visible to the public, present on the internet. So I'm going to leave everything public to avoid complications. Now, it is possible to create publicly visible presentations from private repositories. I don't see the benefit in doing that, but you're welcome to investigate that on your own time if you would like. I'm going to leave everything else here as default. Licensing is an interesting thing to talk about. If you start writing software, all of my software is released under GNU GPL version 3.0, which is the thing that is used for the Linux operating system. The easiest one to use is either MIT or this one, which is, you're not really supposed to use the name Apache if you're not affiliated with the Apache Nation, but they do. And this is, so I call this ASF for the Apache Software Foundation. So the ASF license. And, we'll select MIT for that. Why not? Okay. I'm going to create repository. Many of you have done this before. You have made many repositories, right? Okay. When I start working with this repository, oftentimes what I'm going to want to do is I'm going to want to upload files to it. And so I'm going to demonstrate the process of how I'm going to create the file which I'm going to upload to this and which I am then going to put on the internet. Now, there's a variety of ways to do this. I think the simplest way is to make one file I upload once, and so I'm going to step through that process. I'm going to begin with the provided template file, which is presentation.qmd. If I click here, I've got a lot of niceties going on here and so on, so I'm going to save this. I'm saving it as final present.qmd. That is in my downloads folder on my browser and probably in a similar place on yours. When I open a QMD file, by default, it opens itself up in VS Code. Yours may open itself up in RStudio. I don't think it matters. I'm going to open this in unrestricted mode because I trust myself. I'm going to close this thing just because it's hard to see. You see, we're going to learn about Torch in a little bit. Okay? So I'm going to close this box. Actually, here, let's make this a slightly better example. I'm going to close VS Code, and we're going to open this directly. Okay? And I expect you to see something like this. I am going to manage restricted mode, right? Now, VS Code and RStudio are both integrated development or design. They're IDEs, whatever that stands for. Does someone know what IDE stands for? Integrated Development Environment? Yeah, I don't think it matters. Good job. I would give you a gold star if I had one. But actually, stars are predominantly made of hydrogen. So, I downloaded something that contains executable code off the internet. Should you ever do that? No. Now, I downloaded it from me, and I trust me, and you all can definitely trust me too, right? I think we all agree that I'm trustworthy, right? So there's no concerns here at all, right? So I'm going to go ahead and say, I trust me. Trust. And in a way, this is a team building exercise, right? This is kind of like the trust fall for your computer, right? If you threw your computer at me, would you trust me to catch it? That was a bad example. Okay, so I've trusted myself. When I trusted myself, we'll notice that the syntax highlighting changed a little bit. This is now much, much closer to looking like a classical Markdown document. But you don't have to believe me. We can probably find some code to run here. Can we? Jeez. Oh, there's no code in here because there wasn't supposed to be any code. Here, we can make some. Run cell. Oh, it requires the R extension. Anyways, this is our sort of slideshow technology. Now, I have the Quarto extension installed in VS Code, which you can see right here. And I expect you have this installed in either VS Code or in RStudio by now because I've been asking you to turn in HTML documents, right? So we're familiar with all of that. So what I can do is I can just click preview or whatever you do, however you render, and this will render some HTML document. It's just going to render the document naively wherever I downloaded the final presentation Quarto Markdown, right? It's still thinking. It created a document called finalpresentation.html, and we can even see what it looks like in the preview here, right? This isn't the only place we can see the preview. We also did this in our downloads folder. And that downloads folder is right here in my browser. I can see show all downloads. And now I suspect there's probably going to be an HTML document in here somewhere. Ooh, there's a lot of stuff going on there. Look at that. Let's get rid of all of that. I'm going to look at my downloads document, or downloads, why'd I say document? Downloads directory. This is a folder on my local device. I don't know the best way to find this on macOS, right? And where did this save? Let's see. Final present. There we go. When I searched for final present, I found a few things. And one of the things that I found is this HTML document, right? So we can open that. And this is a locally rendered final presentation document, right? Now, in this class previously, I have talked about some of the limitations of relying on this form of rendering. And one of them was that if I took this document and I copied it to some other directory, such as documents, and I pasted it, I would happen to get, not, is that too small? I can't make it bigger. I don't know how to make it bigger. I don't know how this version of Windows works. Is that too small? Okay, we can see it. When I copied the single file, final present, it also grabbed all of this other stuff, right? And that kind of stresses me out a little bit, because somehow I have to get that stuff on the internet, right? So I have taken to using the embed resources flag. Resources Quarto. Embed resources. Embed resources does not change what the file looks like, but it changes it from having external dependencies, which are those things in that other folder, to not having those external dependencies. And let's take a look at what those external dependencies look like. And the way we do that is through using some, I don't know, arcane process or perhaps alchemy. These things got connected by name, so I'm going to change the name of this. Am I? Do I know how to use that on? Okay. Some other name. I'm going to click yes here. I'm going to move this to pictures, which is currently unused. I'm going to open this. This presentation appears differently because it doesn't have all of the built-in niceties. Now, it mostly looks pretty okay, and in fact, you could present from this if absolutely necessary, but you probably don't want to do that, okay? So, I'm going to delete this. I'm going to delete this. I'm actually going to delete all this stuff. And then what I'm going to do is I'm going to alter my Quarto Markdown document. How? I'm going to change the format slightly. I think I'm going to do that by setting the format and then also having embed resources true. Is that how you're supposed to do it? I'm sure that's fine. I wrote down how to do this somewhere, right? It's in the presentation too. It's literally here. I don't see it. In the instructions link on my website. I've never been to my website. Here? Really? You're not beating the allegations. Okay. It was in one of these, I think. There it is. Embed resources true. Okay, so HTML embed resources true. Reveal JS embed resources true. Okay, I'm going to close the preview, which you don't have to do, and then I'm going to re-render. I'm going to press this button. This should still look the same. We can go to downloads. We can take the same file. Let's see, it was called Final Present, was it not? We're going to copy the HTML file. We're going to put it in Documents. And we notice that it now no longer comes with friends. If I open this here, it looks like a slideshow. It has all the niceties we would expect of a slideshow. And then I'm going to do the next part of the process I did. I'm going to change its name to some other name. I'm going to copy paste it with Control C. I'm going to move to Pictures, Control V, just to show that I can move it safely. And then I am going to open it, and I am going to once again get a presentation. So these are all of the features that I want my presentation to have. I want it to be portable. I want it to be self-contained. I don't want there to be drama, right? I'm going to change the name of this once again to Calvin's presentation. Or what group number am I? I'm probably like team high. I can do whatever I want because I'm in charge. Presentation. Or no, it's final. Final. Okay. And so now I have this document that I can be confident will look the same way no matter where I put it, right? And so, of course, what I do is I put it somewhere. And the somewhere that I'm going to put it, function F11, okay. The somewhere I'm going to put it is on the GitHub repository that I created earlier, which I think is called this one, Demo Final. Looking good, right? I think this looks like a very tasteful repository, right? The shade of green is quite elegant. Got some gray, it's not too bright. The name is stylishly stylized in all lowercases with no spaces, just that little underscore there. Very, very demure. No, shoot. Is that how you say it? Demure? Yeah. It is demure. Okay. So what am I going to do here? I'm going to click my favorite addition operator, the plus button, and I'm going to upload files. Which files am I going to upload? These ones over here that I just made. You can just drag and drop. That's fine. If I couldn't do that, I could choose files, and I could navigate to the same location and get Team Pi Final. I'm going to make some notes to myself. These notes are not mandatory. Adding example presentation as Team Pi Final. Done in class 414. 414? It's a palindrome. That should make it more powerful. A palindrome date. Smiley face. Okay. Leave everything else default. We'll commit those changes. Okay. Now, this is not sufficient to display my slideshow live on the internet. This does not currently correspond to a website. This corresponds to having saved files on the internet. To go to the next step, to go from having saved files on the internet to having a website, I'm going to have to make some configurations to the GitHub repository that are going to turn it into a repository which corresponds to a website, right? I think of this as much the same way as assigning a variable to some value in a programming language. The way I'm going to do that is I'm going to navigate to... Wait, is everyone here? Does anyone want me to stop while you catch up before we go through this process? This is the mission critical part. Are we completely locked in? Okay, I'm clicking settings, right? And I'm holding my hands up to make sure we're all caught up. Okay, this is settings. First we bump, then we settings, then we spike, right? Okay. Any volleyball appreciators? Yeah. I think Team USA like always wins beach volleyball at the Olympics, right? Did I make that up? What does that head movement mean? What other country means? That's budget United States. Okay. And then we go to pages. Why are we going to pages? We're trying to create a web page. I understand there are way too many things on the left-hand side of the screen here. Okay? I get it. GitHub was purchased by Microsoft, and they promptly went to work ruining everything. That's not my fault, okay? I am not more powerful than trillion-dollar corporations. Anyways, I'm going to click Pages. Okay. Once again, there are way too many settings on this. I understand that. What am I going to do about it? Absolutely nothing. I only need to change these two options, right? I'm going to change my branch to the main branch. Why am I going to use the main branch? Well, when I checked in, or uploaded, or saved, or however you want to think of it, my final presentation earlier, I got to decide where to put it. I got to decide if I got to put it on the default branch, was at that time called main, like Main Street, or I got to decide if I put it on another branch. I left it on main branch. I only have main branch. Main branch is the default branch, so I'm just going to use main for everything, and I'm not going to overthink it. If I were a software engineer, I would overthink it and I would derive great joy from that. So if you go into software engineering, you will deal with branches more. In our case, we're just making a website and we don't want to think about all that stuff. So we're just going to do main. Now, we previously talked about file paths and folders and extensions, right? You are under no obligation to just put your slideshow at what I call the top level, or the root, the maximum level of your repository, not inside of any other folders. But if you put it inside any other folder, you're going to have to select which folder you use here. I just put mine right in the middle of the repository without thinking about it at all. So I'm going to just put things right in the middle of the repository without thinking about it at all, right? So then I'm going to save that. And this means my Git pages source has been saved. Now, I think, and I don't remember for sure, but I believe that's all I have to do. I might have to come back here and fiddle with build and deployment, but I think this is going to work. And I'm going to step through how I'm going to check this is going to work. I'm going to look at two different places. The first is code, up at the top, right under where it says CD public demo final. I'm going to click that and I'm going to see if it says there's a corresponding GitHub pages deployment there. That's the first place I'm going to look. The second place I'm going to look is the same place I put code. I'm going to go over to the for position. This is the one indexed for position where it says actions, and I'm going to see if my website is being built from the code I have provided. So I'm going to check those two things and we're going to see if this is working. I'm going to go to code. And I'm seeing I do have a deployment on GitHub pages. That's good. This suggests to me I don't even need to check actions. Let's just click on this right now. Okay, and that took me, actually, I think 2 actions. I think this looks the same. But here's the location, GitHub pages demo final. Okay. When I navigate here, I am getting a 404 file not found. Why is this? Well, I have created a web page, but it doesn't have an index.html, which is where you navigate to by default. So I'm going to need to make some edits to the URL to see the thing I uploaded. Either I can upload my slideshow as index.html, which is the default name, sort of like main is the default name for branches, or I can type the name of my slideshow at the end. I think I called mine final pi present.html. Ooh, that doesn't work. What was it called? Team pi final.html. We'll try it. And there we go. That is my final presentation. Let me show you one other thing. I'm going to try and change the name of this file. I'm going to wait around 15 or 20 seconds while it updates, and then I think I'm going to be able to check it without sort of doing the URL manipulation, okay? So I'm going to come over here. I'm going to click on the name of my slideshow. I'm going to go to the far right-hand side of the screen, and I'm going to click Edit File. How do I know that's where it is? I've done this a lot. Just trust me, you'll get used to it, right? If you aren't sure what to do, the first time I had to edit a file, sort of, on GitHub, I looked up how to change the name of a file, and I read some documentation. It took 5 minutes. It didn't take that long. When I click that button, ooh, all of the file contents went away? That's kind of suspicious. Why did they all go away? That's scary. Okay, I'm going to change this to index.html. We'll just use the defaults for everything. That sure does look like it deleted everything. I'm going to show you what actions looks like, and I'm going to point out 2 different things to you. When I made a new change called a commit to GitHub, it popped up this little description of the change here, and it put like a little orange thing. That orange is denoting that the process of turning this into a website is ongoing. I can click on this and see what's happening, or I can go to Actions and see what actions are taking place. We are currently doing a pages build and deployment, and there are 3 stages to this process: the build, the report build status, and the deploy. I get an email when my builds don't work. You might or might not. And I think, yes. So I think there's a page here, but it's blank. Let's fix this problem. I'm going to go back to code. I'm going to take index.html. I'm going to delete this file. Do I know how to delete it? Probably. Maybe. Maybe not. That's okay. I'm going to take the contents of the original file, which was some other name. I'm going to open it with Visual Studio Code. I'm going to open it. I'm going to copy paste the contents of this file, Control-C, into this folder, or this file. I'm going to commit the changes. This is going to be saved as update, and this is one way to fix things when things go wrong. You can copy paste files back and forth. When I make that change, once again, the website's going to go through the process of building itself, but you don't have to believe me. You can click on code and see what is happening. It is thinking. It is thinking quite hard, I would assume. We can go look at the details. Lots of excitement going on here. Have you all, by any chance, used Docker in your data engineering class? These are all running inside Docker images. Does it say Docker anywhere? There we go, right? So this is a Docker container that is doing all of this work. That is interesting to you. Okay. This is still not working. And there we go. We have it all working. I think this is a relatively nice URL. We can debate the merits of that. But that is my GitHub username.github.io/ the name of the repository I selected. If I navigate to that, it auto-populates by saying title slide, but that's not a huge deal. And there you have this as a publicly visible repository. I'm going to take 2 links now, and I'm going to put them in Discord. I'm going to put this link in here as an example. And then separately, I'm going to link to the repository, which is, to me, this is the repository page where it says code and has the code and everything, right? So I'm going to take this and copy paste that. And then we're going to do one review before we move on. Okay. What is the review? I want to show you how I changed this from just being a repository to being a website. How did I do that? I clicked on Settings, far right side, the top menu. I clicked on Pages, the bottom of maybe the second paragraph on the left side. And then I selected these options. Under branch, I selected main and I selected root. You don't have to select main and root, but if you select something else, you have to know what you're doing, okay? And I think this is all working. Does anyone want to ask me any questions about any steps of that process? Okay. Some of you have seen GitHub pages from me a gazillion times. Was this the best or worst way I've ever explained it? Okay. Do you want... I can give you 10 minutes to talk about this with your group right now, or we can start deep learning. Do you want 10 minutes? No? Okay, wait. Kendall, did you nod yes? Okay, take 10 minutes because I need water, and then we will get cracking, okay? No.
It's your mistake. Yeah, I'm such. But combine. Oh, no. Yeah, I think we can. Okay. It's all. Like Joe Busty, I literally, I don't think that's never coming. That's like a lot of so that's what I was It's I put in the big you know. I look on the bottom, it's just okay.
Only five figures. How can you get it? What's wrong? Yeah. It's the.
It's also help like for sleep, how to do things. Yeah.
That's just the same.
I think when I read mine, that was like. Yeah. You'll have actually for 5 months. Literally, not getting it was in the letters. You're this is a lot of that. There's my own there. I put yeah. Same. Like I can get there. So I got that. How are you? Yeah, at least the majority of people. Yeah. We know as well. Great. I'll take this. Oh. Nice.
Like a flip? Oh. Okay. Enough, but I can back it. Yes. Oh, okay. And we're doing it like with some passenger here. I think it's like we're gonna do that. Yes. Yeah, it's not. Yep, yep. Oh, I think I done the version.
We have.
Thanks for the next. I think from all your choices. It was really like last night. I was like, my friends, they're very long time. Sorry. See what's the house. My friends, wasn't long. And he calls us here. I don't call the same. And Landon was saying, obviously, it was like, they were on the thing. I do this for the areas. It's very actually. It's very. Told me they were coming. Told me they. Yeah. Right? Yeah. You know, it's a, if we could just be. It's just saying, the department, listening to us, context, so it's not as easy to offer this, stuff, and it's cultural. I mean, it's a we can get different because they're seasons. Oh, yeah. So the things are Mars, so Robert will be female, focusing on like the progressive of this. So we basically it's my you can search it. It's like it's gonna use natural language processing. So yeah, make I remember it. That's like we're gonna show it. Yeah, it's like you can generate around and like you basic analytics. That's what I done. And I have no idea how I would need to set it up. But I'm gonna. Like I was on a time over and can just take them some technical too. Real. Yeah. The reason why they're It's an absolute shame thing. Oh, they are a lot of really bad on there now. They forget. I don't know if it's a little bit of it. So, and really one time it gets to us before we can see the 35 was exactly like growth. See that we have. I love some more. It's like it's the only word I see next. Touch on. I mean, that makes only touch some action. It's the right one of us is sharing. The engineering. Files that coming up my take and then once I was I was like, could you just feel yeah. Yeah. And they're all sad. And it's okay. Then there was more. And then Judas on fire and then it does. Yeah. But yeah. Yes, and that's what I'm saying. Like especially students. Or I had even come up and say. Like another question. We understand it. All I know is I was logging a lot of hours. I do get points about this. Oh, that's where the semester. Like this, like you're asking me to push still like this, like my two guys did this. But then there's a lot of people that have to be really hard semester, and then they're like. They're probably under like pretty people who on the way that they're doing. That's like honestly, who can actually, you know, the person. And then literally on Saturday, the guy from Brother Martin stopped like his sure and they were supposed to present this stuff. And so they ended up playing but it's yeah. But they're like racing nothing is not for their turn, but like we're not gonna dump them because they don't care. But you do your best to cheat. Because they're presenting to the company. Their final is presenting to us. With party. I know like they don't want like they somebody knows like they've been talking like every treatment thing. I mean, it's not like they just didn't know where their product was and they presented it like this. Like they literally known about it every single cycle. Like yeah, it looks great. They're not everybody has to get fired. I'm so lucky that it's like all of these ones. So they had this internship. The food will really it's very working for in like in the craft course, yeah, no, they pay for a button run. No, I just started. You feel good. Yeah. Exactly. See, around. It's like this. You'll get Yeah. I
Neural networks. So, legend has it, in like the 40s to 70s, the first cognitive scientists, then maybe they were starting to be called computer scientists in that era, and maybe like like regular scientists, like people that do science, were getting together and they were like, I bet a computer can think, right? We can probably knock this problem out in like 18 months or something. And they did. They wrote Lisp processing, the greatest programming language, and then they should have just been done and all gone home, right? But for some reason, they kept doing things after that, right? And one of the first initial insights into the idea of machines that think, or computers that think, or devices that think, right, was the idea of the neural network. So some of the early computer scientists were talking to biologists, and I guess I don't know when biologists got really into neuroscience or when that happened, right? But at some point in time, I believe basically imaging technology became good enough that you could look at neurological tissue and see that there's neurons in it, right? And a neuron is basically a cell, and it's a cell that obviously stores a Boolean value, true, false, right? We're all familiar with cells that hold Boolean values, right? And the Boolean value corresponds to whether the cell activates and creates an electric charge or not. And all of these cells talk to each other by communicating electric charges down their dendrites, then releasing something called a neurotransmitter. And that's what my brain makes when I drink an oat milk mocha. It makes a bunch of neurotransmitters, and then I feel happy, right? When I was but a wee child, just a tiny, like small human, like of below average size, right? Now I'm roughly average size, right? I remember reading, I think on the front page of National Geographic, there was a headline that said, "Can a single neuron recognize Bill Clinton?" And for those of you that don't know, Bill Clinton was a recurring character on reality television in the 90s, right? And so, could a single neuron recognize Bill Clinton? And that was significant to me because that's the first time I remember seeing the term neuron in popular culture. And a single neuron recognizing Bill Clinton should mean that neuron sets its value to true, activates, triggers an electric impulse, and releases some corresponding neurotransmitters when the vision framework detects something that looks an awful lot like Bill Clinton, right? That's how I understand neural networks, very heavily inspired by biology. Now, in the 70s, right up until I think 2014, when these things started working again, it was widely considered that the costs of emulating a neural network in computers were quite high. This seemed like an unreasonable way to answer questions that we had about things like, is this a picture of a duck, or of Bill Clinton, or of a slideshow, or of GitHub pages, or of a Zamboni, my favorite thing to look at pictures of, right? And so neural networks fell out of favor for, I think, like a generation of science, right, basically. And they're back now. Now they're the only thing that work. They seem great. The LLMs are close enough to seeming like neural networks. You can think of them as neural networks. No one will stop you. But there's been considerable mathematical and sort of philosophical improvements to the ways we think about neural networks, as well as the hardware improvements from more advanced modern technology, specifically the graphics processing. So that's my introduction to the idea of neural networks. Neural networks are the basis of deep learning. I, for many years, thought it was not machine learning unless it was a neural network. You don't have to think that, but you're allowed to think that if you want to. I think that's probably a defensible posture. So, how does this work? When I think a thought in my brain, what I think happens is I have a bunch of neurons that correspond to concepts or ideas or feelings. right? I don't know if that's true. I don't think it matters if that's true. That's what it feels like. When I am thinking about linear algebra, it feels like I'm in a different sort of cognitive space than when I think about crossword puzzles, even though both of those things concern 2x2 grids, right? And so, cognitively, I imagine myself and I perceive my own intelligence as if it's just a combination of neurons that either say yes or no in response to certain stimuli, and somehow the stimuli filters to those neurons from my senses. Now, when I think of it that way, that somehow things come in through my eyes and my ears and my buccal snoot, which is what I call my nose, I don't actually use my mouth for anything other than yabbering, so nothing goes into my mouth. I simply absorb atmospheric moisture and then run on cold fusion. But when I perceive things, I think of it this way, that there's a bunch of neurons that toggle true, false, and then they talk to each other and toggle true, false, and all those true, falses come together to cause me to do things like move my hands and yabber and do all of the things that like my muscles and so on do, right? This is oddly similar to a very high-level description of a computer. A computer receives inputs primarily from a mouse, a keyboard, and from the internet, right, coming over Wi-Fi, so it has perhaps 3 senses. Inside of the computer, there's a bunch of little transistors. There's probably, I don't know, 7 billion of them or something, which is probably pretty similar to the number of cells in my brain, right? And each of those little transistors, which is just a little digital circuit, it either contains a positively or negatively charged charge, right? And that's starting to feel an awful lot like a neuron. And then we look at, well, what is actually going on in those computers? Well, there's a bunch of wires connecting all these transistors to each other. Well, all the neurons in my brain are connected to each other with dendrites, these sort of long spindly things that actually even transmit electrical impulses, right? So what is the fundamental difference between my brain and a neural network or a computer? And it's like, well, there are implementation differences, but philosophically, there seems to be relatively few differences, right? And this got much more pronounced with the rise of graphics processing units. Why is that? Graphics is fundamentally a realm of approximation. When I look at my screen and I have 1920 by 1080 pixels, that's 2 million pixels, right? 2,000 times 1,000. I can't see 2 million of anything, which means that if the color of one of those is off by 1%, I don't perceive it. Graphics processing units became highly optimized to compute the values of large numbers of pixels all at once. They were masters of approximation. My brain is also a master of approximation. I do not know how many inches I am from Portland. I know how many hours I am from Portland. I know an approximate result. And I believe the way I think about this and perceive this is the neurons in my mind are good at answering true-false questions, and they're not very good at storing numbers with 6 sort of figures of precision, right? I don't know a lot of numbers that are 5 digits long. I find it relatively hard to memorize phone numbers compared to colors, right? These things just seem difficult to me. So GPUs, as masters of approximation and doing large numbers of approximate calculation, seem much closer to the way my brain seems to feel. Separately, it seems to me like most of what humans do and are pretty good at, we seem very heavily visual. We seem to use our eyes for a lot of things, right? And over time, we sort of grind the life out of young people and force them to read books, right? Can I hear it for books? Yeah, and who would rather read a book than watch an anime? Exactly, no one. No, stop cheering. Okay. That was a trick question. You all love anime, right? Okay. Do we have product placement? Okay. All right, shout out Weaves. Okay, so it seems like humans are heavily visual. Graphics processing units were optimized for visual sort of cognitive loads. Okay, fair enough. It shouldn't be that alarming to us that when we design computers to specifically do things that people like, they seem to get better at thinking the way we perceive humans as to think. Now, again, I want to point out, my understanding of the biology is they found out that none of this neural network stuff actually makes any sense at all, and no one cares. Because it doesn't matter if it's correct, it matters if it works, right? And it happens to work really well, which you can verify by going on Facebook and seeing if anyone can tell the difference between AI and non-AI generated art, right? I can't even tell the difference between human and other human generated art. Was I going anywhere with that? No. Human generated art and human generated non-art. That's what I was going to say. What makes art, right? Great question. Okay. So, how do we often perceive this in terms of computers? Now, again, the modern neural networks, the 2025 neural networks, I think are considerably more sophisticated than this. And again, that doesn't matter because we just need a framework to think about them. I'm going to think about them today in terms of 3 parts, one of which corresponds to a single layer, one of which corresponds to a bunch of stuff, and then sort of an output layer. So what is the input layer? The input layer is essentially the entries to a data frame. I always think of the input layer to a neural network as being an image because of my background in computer vision. So what I think of as the inputs to any sort of thinking is the sort of pixel space that comes in through my eye, right? And at sort of each location within my eye, I either get a yes, no result to how bright something is, perhaps in the red, green, and blue spectrum, right? And that's sort of the input I see. It is much easier to think of this in terms of perceiving text. When I look at text on a page, there is either text data or blank space there, right? Usually either in this case, we have white on black, or on the page, we have black on white, right? Very visually simple. So we can think of perhaps even this slide as a matrix, right? Where some values are populated and some values are unpopulated, and that is the input to a neural network. Then there's a bunch of stuff. That's the hidden layers. The hidden layers are sort of the internal complexities of the connections between neurons in my brain. And then there's the output layers. On a computer, the output layers often themselves correspond to a data frame or perhaps a screen. In the case of my brain, the output layers correspond to inputs to a variety of muscles, basically, right? And essentially there's, something that drives this muscle in my jaw that causes me to speak. And there's a lot of small neurons that control synapses that correspond to something muscles. I don't know how biology works, right? And so you provide stimulus, some abstract complex process happens, and then a bunch of wires come out of it, and some of the wires are saying yes, and some of the wires are saying no. So that's how we perceive this. Is this easier to look at with a picture? Yes, probably. We're going to differentiate sort of 2 different kinds of ways we get through a neural network. This is basically forward and backward propagation. So we're going to begin with a discussion of forward pass. When I say forward pass, why do I also say activation function? The forward pass through a neural network begins with information arriving at the input layer, the first layer. And that information causes certain neurons, or the idea of neurons, to activate and to go from false to true, to carry some value, right? Now, somehow each one of those neurons has to decide whether it activates or not in the presence of some stimulus, or some observation, or some input, or someone typing something on a computer, or some signal coming over Wi-Fi, right? That is an activation function. So when we go forward through a neural network, we're going forward in the context of the network, but we are activating in the context of a single neuron. This slide claims in the second line of the first bullet point that computations are performed layer by layer until the output is generated. Computation is sort of an abstract theoretical thought here. What is going on is some output layer is going to output a bunch of true-false values in some way. We're going to perceive or understand or interpret that information in any given way, right? Perhaps as a number, perhaps as a series of instructions, perhaps as a graphic. It does not matter. But internally, a bunch of changes are going to be made to the input values to generate some output values, right? That's the forward pass. Activation functions are what individual neurons, individual true-false values do. Now, how does a neuron make these different true-false values? Well, in my brain, each neuron is hooked up to some other neurons. Not every neuron, in fact, a very small percentage of the neurons, but every neuron is connected to some other neurons, right? And so when 7 neurons in my brain activate, they're going to touch 50 other neurons, and some of those neurons will choose to activate or not based on how good friends they are with each other, right? This should begin to you to sound an awful lot like a discussion of linear combinations. When a linear combinations of neurons fire, that determines whether some other neurons fire and some other neurons fire. And these are the hidden layers that progress from the input layer to the output layer. We can interpret neural networks as doing something akin to feature engineering. How? Well, the input layer can be an observation, and that observation can be a series of true-false values, such as encoding categorical variables, or those true-false values can encode in binary some numerical value. It makes no difference to us. We're just throwing this into a black box computation engine, right? When we take that input observation and we run it through some neural network, and we get some output at the end that might say Pinot Noir, Pinot Gris, Chardonnay, or it might say Oregon or California, or it might say California or not, right? Or it might say a variety of things. It might say a price value, right? What is actually going on is in sort of those intermediate layers between the input and the output, it is quite likely that some of the value that comes on the input is being thrown out or discarded or not cared about. And we don't necessarily perceive the loss of that data. The only thing we see is the output. So we can think of this as a technique for automatic feature engineering. And in that sense, that is why deep learning appears in the unsupervised learning part of this class, where we've been making these discussions of how do we determine which features we care about, can we synthesize new features, right? This is an awful lot like PCR without actually doing math, just taking a bunch of true-false values and hoping it works. This is one way to visualize what it looks like. We could, for example, have an input that has 4 true-false values. For example, with a wine, it could be white, red, Oregon or bad. That was a joke. Everyone catch that? Anyone love the Walla Walla Valley? How about, can I get a cheer for the great state of Marlborough? Okay, no. Fair enough. Okay. We got red, white, Oregon bad, Pinot Noir or not, and then 95 or higher or not. We scramble this up, and each of these neurons has a series of other connections, right? These are meant to look a little bit random, right? So red or white connects to the first, second, and fourth neuron in the second row. Oregon or not connects to, looks like just the second and third, right? So we input these features, and then we sort of weight them together. So this sort of first value here is a linear combination of the third value and the first value. The second one is a linear combination of the first and the second, and so on. All of these connections are just determined randomly. We randomly seed them and we try different things and we see what happens, right? So this hidden layer is going to be a bunch of linear combinations of the input layer. We can have as many hidden layers as we want. In this example, there is a single hidden layer, right? And then we have some output layer. This might say 90 or higher, $30 or higher. I don't know what other features wine has. Is delicious. Is available at Safeway, right? Do y'all get your groceries at Safeway? Where do we get our groceries? Are we a Winco class? I love Winco. Oh, we don't like Safeway? Safeway, more like no way. Yeah. The people that are scared of cities that live near me refer to the downtown Safeway as the unsafe way, which I think is hilarious because they don't bother me when I go there. Okay. I call it the safe way because okay. Anyways, and so we get some output values in this output layer, right? The common example with digit classification, so you recognize things 0 through 9, right? Is you just have 9 output values. And they output at different levels of yesness, right? And so whatever the highest output value is, you say, oh, that's a 7. That's a 6, right? In this case, maybe we're recognizing whether wines are 1, 2, 3, or 4, right? So this is an example of what a neural network looks like. I think I owe you all an apology. This is ugly to have this on a white on a black background. What I think I should have done is I should have inverted the colors on this. And that probably would have looked fine, right? I'm not. We're not going to do web development right now. Don't let me stop. Okay, cutting me off. Okay. What is a neuron? Well, it determines a true-false value, but it determines that true-false value based off of a linear combination. Yay! Who loves linear combinations? That's what I thought. I thought we all loved linear combinations, right? So we have a series of input features or values, right? We could take the weighted sum over all of them. So we take a weighting argument, w sub I, which is that I correspond to, that corresponds to the input value. What do these correspond to on this graph? Well, this is one input value coming from this input layer thing. We're going to weight this. So a 1 is going to come out of this, or a 0, depending on whether this neuron activates, right? But maybe we only 50% care if this neuron activates. And maybe this one over here, we 75% care if it activates, right? So we're going to add up. If this first one activates, we're going to take a 0.5. And if this one activates, we're going to take a 0.75. We're going to add those together and we're going to get 1.25. And that's going to be our activation level, right? So we can take a weighted sum across the inputs. And maybe we have some bias value. So if everything comes in and I have something weighted at 0.5 and something weighted at 0.75, well, that means I can score as high as 1.25. That's way too high, right? I'm working way too hard there, right? So maybe I add a negative 0.25 to that or something, and then I just round or something like this. So oftentimes we just calculate this value, this linear combination with an offset, right? And then we just say, oh, if that's over or under a certain value, then we can say that the neuron activates. How do we do that? Well, oftentimes we take this value, the weighted sum, and we apply some function to it. What's an example of a function we can take over one variable and return some other numerical value? We could, for example, say this is the negation function. We could give a 7 and this could return a negative 7. We probably don't want to do that, right? We could square. Basically everything we do to a bias or a loss function we can do to this thing. Usually these are nonlinear functions. And the physicists got really into machine learning there for a few years because they knew a bunch of nonlinear functions from whatever it is physicists do. Any physicists in here? Anyone heard of a logarithm? Those logarithms, those are nonlinear, right? So you are all basically chaos theorists, right? So put that on your resume, right? So we're going to take a linear combination of inputs with weights and biases, and we're going to do some chaos theory. Does everyone love Tom Clancy's Splinter Cell Chaos Theory? Is that a book? Movie? It's a book. I love books. I love reading. So once again, I owe you an apology. This obviously should be color inverted, right? So what's this look like? Okay. I got my inputs. In severance, these are called innies, right? That didn't make sense. Don't think that made sense, right? Okay. So we've got some inputs. The inputs are the colors that hit my retina, right? So maybe I'm getting some like wood tones over there. Maybe I'm getting some like exposed concrete right here. I'm like, ooh, this is like a very chic room. It's like the overall activation I'm getting, right? We love Ford 102, don't we, folks? Okay. So then we apply a weight to each of them. So I apply a very low weight to my peripheral vision because I can't see what's going on over there. And I apply a very high weight to the center of my vision, right? So we have our inputs. We have our weights. We combine these things. We take a sum over the product of an input and a weight and the product of an input and a weight, sum them up, put them in a transfer function, right? That comes into our activation function. So we do products, sums, nonlinear function, and then we either activate or don't activate, and we have an input here determining a threshold. Our activation function has to exceed some threshold in order for the neuron to activate. Remember, these things are true-false. They do not output a numerical value. They output only a true-false value, which means if they achieve some numerical value, we have to somehow split that. Y'all remember logistic regression? Where we took numbers and we turned them into true-falses? Yeah. That's what neurons do all day. So your brain actually runs on logistic regression. That's why you're so logical. Oops, I clicked a button. Wait, hold on. No, stop. This is supposed to be on a transparent background, right? So why is it on a white background here? That means I had to make the design decision to put this on a white background. What's wrong with me? Yeah, but what if I inverted all the colors? I feel like my sense of design and style has just been so off lately, right? I'm surprised you haven't said anything. Um, and let's do activation functions, and we're getting up to the cool thing I was building up to before dinner. So get ready to hold on to your hats because I'm gonna blow them clean off, right? This is gonna be so cool. I am unbelievably hyped. Yeah, hold on. That thing could go anywhere, right? As soon as the neurons in your brain activate. This is anyone's guess. Okay. So the coolest, I think the kids these days are saying based, the most based activation function, right? Is the sigmoid. A lot of people don't know this, but sigma grind sets are named after this function, right? And so I have no idea why it's called the sigmoid, actually. I've never even thought, why is it called the sigmoid? This is an S-shaped curve maxing input to a range between 0 and 1. It is used in binary classification tasks like logistic regression. This is how it works. Take the z, we throw the z into a negative power of e, and what does this look like? Oh, it's time for a throwback. It's time for a throwback. This is gonna blow my mind. I don't know if you care about this. Oh my gosh, it's my machine learning homework from 10 years ago. Oh my gosh, this is the very first question I had on my first machine learning class assignment I ever took. I had to calculate a sigmoid and plot it in MATLAB. That's how fundamental this is to machine learning. When I was learning machine learning, it was literally just sigmoid function. This is all you did all day, right? And so this thing ranges from 0 to 1, given some input values. So what are these z values? These z values are supposed to be the weighted sum of the inputs, right? So maybe our 5 best friends, we all weight them equally, right? We weight them at 1, and they all tell us to not do something, right? But then our haters, which we weight slightly higher. So we have one hater we weight at a value of 5. That person tells us to do the thing, which is probably like play in traffic or something, right? So wow, we get a really high weight and we go up here and we activate, right? And then all you do is you pick an activation threshold somewhere around this. And if you go over that threshold, then the weighted sum is high enough, and that's that. Wow, this is so cool. What a beautiful PDF. I wonder what else is going on in here. Ah, look at all those files. Okay, this is how you know how GitHub works. Okay. Back. Anyways, this is how it looks according to Wikipedia. See, other people have done this as well. Oh, and it's called a logistic curve, right? So secretly, that whole time you were learning about logistic regression, you were actually learning about neuron activation potential. Incredible. I don't know what to do about this. I'm so overhyped. I need to take a break and go eat dinner for exactly 30 minutes and come back and collect my thoughts and feelings. So I hope you don't do anything too outlandish while I'm gone, right? But I need to go touch grass. Oh my gosh, there's the softmax. Okay, we're gonna stop. Okay. All right. How's everyone doing? The recording quality is going to be terrible. That's okay. Jason never. No, it's people in that room. Yeah, so people if I knew.
And they're not, I think so. Being that section, you're not obviously in the second.
Wait, okay, so I don't actually need to be projecting right now, so I can move the podium further.
Your case has been on the,
Yeah, now people are gonna know who I am, right? Face reveal.
oh. Well,
Yeah.
you're an individual, you're a trainer, you're now. Yeah,
There's actually already pictures of my face on the internet. A lot of people. I don't see a way to not just board talk this next part, so I'm just gonna do it. What is that? Why did I go to finite automata and regular languages? That's not what I was trying to move to.
Oh, sorry. Sorry.
Okay. Why is that one not working?
BDIB.
Okay. So the motivating example. Oh, the time delay is going to be super weird. Okay, that's fine. I have talked about the idea of input layers. And I have talked about the motivating example of computer vision, right? Is it weirder to have me up?
Really true. It's easier.
Oh, I can't do that because I don't have a long enough cable. Yeah. Do you want it on or off? Okay, cool. We'll keep going. So, the example of computer vision. And what is the example of computer vision? Well, I'm actually not going to talk necessarily about computers for a moment. I'm just going to talk about the idea of vision and neural networks, right? So we're going to imagine, for the sake of this example, that my eye contains an exactly and a 3x3 grid of rods. Now, I don't know a lot about biology, but my understanding is the rods are the things that percept lightness and darkness, right? So we're going to imagine my eye has a 3x3 grid of these, right? And so we're going to break it out. Is this visible? Too light, too dark? Little too light? Better? No? Okay. Check that marker. That one looks darker. All right, let's try that one. Relatively good?
Yeah.
Okay. So we're going to imagine that my eye has relatively low visual acuity relative to, like, for example, the number of pixels on this monitor. And we're going to say it is simply a 3x3 grid. And we're going to imagine that each element of this grid either says only true or false, right? We're just going to have yes, no. And we're also going to imagine we live in a very restrictive universe we live in a two-dimensional universe named Yahtzee, and the only thing we can see is six-sided die, and because it's two-dimensional, we can only see one side of the die at a time. So here's an example of one thing we can see in our universe. We can see a perfect square. It is incidentally a perfect square, and it exactly fits in our field of view. And it can have, for example, 6 dots on it. And when I percept with my eye this six-sided die, I sort of percept it as imagining that I overlay the grid on here. Now, the first time I started writing programs, I wrote them in the first LEGO League in a middle school competition doing robotics. And the sensors that a LEGO robot had at that time was it had a touch sensor, a rotation sensor, and a light sensor. The way the light sensor looked is it had a relatively narrow field of view, and it averaged the brightness over this field of view. So, if I had a light sensor, and I looked at this box, I would see a very light shade of gray, because there is a tiny bit of black in it, right? And if I were to look at this box, I would see exactly white. So we can imagine, then, from the perception of my rods and cones, I perceive something a bit like this. Some light gray in each of these boxes. Nothing in the 3 middle boxes. And then some light gray in each of these boxes, right? So that makes sense in terms of perception if I have low granularity perception, right? Okay, now, I have arranged these in 2-dimensional space, but I can also think of them as existing in 1-dimensional space as a simple vector. Why can I think of it that way? Well, perhaps whatever is going on in here, I simply have neurons hooking them up that happen to go in order. Let me show you an example. We take this neuron, and it goes to one box. And then we take this neuron, it goes to another. And we simply proceed either row-wise or column-wise across, right? And so we project this into one space. I'm going to draw more boxes. Let's see, that is 4, 5, 6, 7, 8, and 9. I was doing, is it called column major order when you do columns first? Is it more confusing to do rows or columns? I'm just going to stack these up, okay? So we're going to imagine that my input layer as just the first row. This marker is very strongly scented, and it does not smell like an oat milk mocha. Okay. Which no one asked me, but that's what I thought it should smell like. So I was talking to the barista at my oat milk mocha place. This is unrelated. And we realized, so I walk in every day and I order a small, hot oat milk mocha to go. But we can take an initialism of that. We can call it mocha, oat, to go, hot, small, and then we can call that moths, right? So I drank moths, right? Isn't that cool? Okay, so anyways, we can perceive this as an input layer to a neural network, right? And then within that neural network, we can have a series of internal neurons, right? And so we don't necessarily know how many neurons we're going to have, right? So I'll just put, we'll do 5 for now. Now we'll do 7. Okay. Now, we imagine that we may want to perform some classification tests, right? Perhaps we want to differentiate a 6, a die denoting 6. Is that how I would say this? The 6 face of a dice. Does anyone know anything about dice? Any Yahtzee players? Anyone play D&D? Yeah. Okay, this is a D6. What do we call the 6th face of a D6? Yeah, right. I don't know either, right? Okay. I think the next best number after 6, of course, is 3. We can all understand that. It's the first odd prime number, right? Which everyone loves, right? And so that looks something like this, which would correspond to a different layer. So for example, if I were to do this and break it out the same way, you have a gray. No, we don't have a gray in that position. We have a gray in the 3rd position. 3, 3, Oh, that's way too big. Okay. We have gray in the third position, gray in the middle of the next row, gray in the leading position of the final row, right? And so each of these input layers are going to go into our hidden layer in some way, right? Okay. And then what we want is we want some output layer. I'm out of board space already. Let's see, I can move this. Everyone close your eyes. I'm going to get motion sickness when I do this. Sit down. It's like there's an earthquake. One of the MSDS students is in San Diego this morning, and if there's 2 caps. You see this? I don't believe you. I think there's only 1 marker. My computer vision frame cannot differentiate these 2 markers. I tried to use my touch sensor there, it didn't work. Okay, so what we can do then is we can say, all right, well, somehow we have our vector of size 9. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Rather than doing shading, I'm just going to denote these with either X's or 1s. So for 6, we feed this into some neural network. And what we really want is some way to create combinations of these such that we get outputs, perhaps in another vector, where we either get something denoted 1, 2, 3, 4, 5, or 6. Now, I think we can perceive this as not being the most challenging statistical task to pull off of. And we can look at it in the following way. I think these are how we do dice, and I'm going to do 2 by 3. Does that look right? Is that how you do a 3? Has anyone ever seen a die before?
Yeah.
I feel like I spent more time playing Yahtzee than all of you. Like, y'all don't seem extremely like hyped about Yahtzee, right?
That's great.
It's a great game, right? Everyone loves Yahtzee, right? Yeah, let's hear for Yahtzee, right? Yeah. Yeah, I love yelling. Okay. Okay. So there's probably some way we can train neurons to pick up on these combinations of things, right? So here is one example. I have these 6 neurons. 1, 2, 3, 4, 5, 6. And we have our 9 positions. 1, 2, 3, 4, 5, 6, 7, 8. Well, if we have a 1 dot, that 1 dot will be in position. I have to write numbers on this to have some indexing, so I'm not counting across. I'm going to 1 index this array on the top outside of the array just for the sake of denoting things, right? So we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So if I have a dot in position 5, then I am strongly correlated with getting a 1. However, I could also be correlated with getting a 3 or a 5. So I'm going to put a positive weight on this, and then I'm going to assign strong negative weights to the corners. Because if I'm trying to get a 1, that means I shouldn't have any coloration detected in the corner, right? So we're also going to add negative weights here, and I'm not going to draw the rest. Probably actually those 2 are sufficient, right? For either 5 or 3, one of these 2 positions will be populated. Right? For 2, I actually need exactly 2 corner positions, but not 4. That is extremely non-trivial. That requires a second hidden layer. This is called the XOR problem. Look it up on your own time. I cannot teach it on the board because it's too confusing. But what we can say is, well, we want positive weights coming from the corners. These are the corners. And then we somehow need some sense of negative weight coming from somewhere else, right? So really we need positive weight on two corners and negative weight on two corners or vice versa, right? 3 is actually the combination of these two things, right? Or we can say, oh, we need the corners and something. 6 is not too bad. The only dots that are populated in 6 and not other dots are the so I was at a birthday party this weekend and they said, do you want a corner, an edge, or a center, right? 6 has edges in addition to corners, which means if you see a dot in an edge location, that means you have a 6, right? 8 is an edge location, corresponds to this edge location. That is location 6, 4, and 2. So this is 8, 6, 4, and 2. Does that make sense? So what we can think of this as is 6 is a vector that assigns weights to various input values. It assigns a 0 to position 1, a 1 to position 2, a 0 to position 3, a 1 to position 4. This is position 4. 5 is 0. 6 is 1. 7 is 0. 8 is 1. And 9 is 0. Right? I don't know the way you like denoting vectors. Should I do like this? Is that good? Is this wrong?
0, 1, 0, 1, 0, 1, 0, 0, like feels wrong. It'll be 1, 0, 1, 1, 0.
I was trying to only get edges. Does this only get edges? Yeah. Because the corners can also be present in 2, 3, 4, and 5. Is that right? It doesn't matter, right? It makes sense. Yeah. Because, remember, I don't have to detect if all 6 dots are set. I only have to detect if that is a 6. Right. And this is how a computer vision framework works in my mind. This is an extremely restrictive example. Let's take a little bit more look at the 2 case, okay? So we're gonna delete this and we're only going to look at 2. Okay. So when I think of 2, I think it looks like this. Or I was allowing rotations. I didn't say this. I don't think it matters. But it can also look like that, right? I haven't made claims about the rotations of my dice. You could do that if you want to make a simplifying assumption, right? And so what this means is that if I count that as position 3, 4, 5, 6, and 7. So we take 3 and 7. 1, 2, 3, 4, 5, 6, 7. And erase this. Well, what we would like to do is we'd like to have 3 and 7 have strong positive weight going into the 2 neuron, right? And that doesn't work because 4, 5, and 6 also have those same values, right? So somehow we have to differentiate this from 4, 5, and 6. And the biggest problem we have is differentiating this from 4. And why is that? Well, these things are linear combinations, which means what we're really computing are lines. If I take, for example, some XY coordinate grid, and it doesn't matter where the origin is located on this grid, but I'm going to interpret the origin as located right here by convention. I can have this be a 2, in which case I need to take the linear combination, which I'm going to call y equals x, right? And the other possible linear combination I have is something like this, which is going to be y equals negative x plus b, which is probably plus 3, right? Um, there is no line that captures this combination of points and that combination of points without capturing any of this combination of points. So that makes sense, right? So what we need is we need an additional hidden layer. So I'm going to create an additional hidden layer. What am I going to do? Well, I'm going to create an intermediate feature. One, two, three, four, five, six, seven, eight. We're going to imagine for a moment we only have 2 neurons in our first layer. As a simplifying assumption, we can simply add this to our other neurons, right? 1 neuron is going to be highly positively correlated with 3 and 7. We're going to take a positive on each of these, and it is going to be highly negatively correlated with 1 and 9, the other 2 corners. This is going to differentiate 2 from 4 in one of the 2 directions, right? So I'm going to put negatives here, and I'm going to put the negatives in parens so it's clear what their orientation is, because I have bad handwriting, right? So I'm going to do negative, but I'm going to put it in parens, right? Okay. I'm going to make 1 additional neuron. This is going to be strongly positively correlated with 9 and with 1, and is going to be strongly negatively correlated with 3 and with 7. I'm going to denote these as hidden neurons. We'll just call them H1 and H2, right? Hidden 1 and hidden 2. So hidden sub 1 is going to be negative x1 plus x3 plus x7 minus x9. Just calling the input x, we'll call this x for some reason. I don't know. So that fine notationally, right? And then we take hidden neuron 2. And this is x1 minus x3 minus x7 plus x9. Okay? Close the parens. I'm going to create 1 additional hidden layer neuron. This is going to be the 4 corners neuron, right? And so this is just going to be the combination of all of these. So we'll take positive across 1, 3, 7, and 9. And I'm going to note that H4C for 4 corners. This is x1 plus x3 plus x7 plus x9. The only thing I really have to do is I have to differentiate 2 from 4, right? So we're going to note 2. What is this going to be? This is going to be the, probably what? We want the maximum of H1 and H2. So this will be strongly positive if we have a 4. So we're going to subtract that. We want a strong negative value. So we'll do H1 plus H2 minus H4C. So we add a negative weight to getting 4, and we add positive weights to both of these things. Then I think all you have to do is set values on these such that this works out. Yeah.
Well, B also return the same thing.
Yes, right? And so how do I solve that? I add an additional neuron that checks to see if the center is set, right? So we also add H center. And that's literally only going to be x5. And that is set for all odd values. So something is 3 if it is highly 2 and highly odd. And I can do that with an additional layer, or I can do it all with one layer, right? I think that's all I'm going to say about that. Does that make sense? Okay. I think I have to assign some weights to this. How am I going to do that? Let's see. This thing is 4 in this position, -4 in this position. This thing is -4 in this position and +4 in that position. And this thing is 4 in these positions, and otherwise it is 2. You just have to multiply these by something, and I can't solve the linear combination while I'm standing here in front of you. But I think what you have to do is add 4 here, and then like multiply these by 2 or something. And then you draw a cutoff at like 6. Can you figure that out? Do I need to do that math? Uh-oh, your eyes are looking glazed over. This makes perfect sense, right?
Sure.
Okay, I'm gonna do the math. Okay. Yeah.
So the x is in values of 1 or -1.
We can put it on any weights. I was only doing linear combinations over 1 here. I could put coefficients in there that are.
Yeah.
Okay. So yeah, let's figure this out. So H1 of this value is, how should I denote this resolves to 4? Would you do, is that fine? Do we want equal? Do you want single equals? Give me some. How's everyone doing today? Can I get like a thumbs up for single equals and a thumbs down for arrow? We like single equals, okay. Okay. So the naive sum of these is 2. And then we can do the same thing. If we have this one, let's see, so we can say H1 plus H2 plus H4C of either this. I'm going to do logical OR with a vertical bar. These both resolve to exactly 2. Okay? And then if I do the same thing on 4, that is going to be 0, which means H2 is going to be 0. And then H3 is going to be 4. So, if I want to construct the feature is 2, you need to multiply these by something, right? Do I? Let's see. Maybe I need one more feature. What more features would I need? I don't think I need another feature. You can just do a maximum, and that's fine. One of the activation functions that I haven't shown you yet, I've only shown you sigmoid. But remember, right before dinner, I showed you softmax. That's where you just take the maximum value. So if you do the maximum of this and say it has to be 4, then you get 2. But we can say if the sum of this thing, h1 plus h2 plus h4c, is greater than 1, then we resolve that to 2. And what we can do here is this a linear combination of each other? No, right? Because I can put a strong multiplier on one of these. If I put like 4 times this, then this resolves to 4 only if we get over 8, and this resolves to 2 if we get to 8. So that gives us an output of 2. And h1 plus h2 plus h4c. I multiply that by 4. Greater than 16. We'll do greater than or equal. That gives us a value of 4. Okay, so we can strongly weight the is4 value. And then if we have a dramatically higher is4 value, then we definitely have 4. If we have a lower is4 value, then we have 2.
Greater than or equal to 16, right?
Yep.
That's something you miss on.
Yeah, and like, does it have to be? No, we can do 14 here. It's
Okay.
not, like, it doesn't matter. There's just some threshold somewhere. And these are supposed to all be nonlinear.
I'm just trying to make sure there's a threshold by if it's.
Yeah.
If the podium cut off the equal sign at the bottom, all of a sudden.
These blasted podiums, right? Yeah. I always try and get 4th place to avoid the podium. A lot of people don't know that trick. Okay. Have I convinced you need 2 layers in your neural network? Okay. Have I convinced you that you can take an output layer and use it to give you a categorical value? In this case, the categorical values are numerical, but it doesn't really matter, right? There is nothing about a 6 on a dice that makes it bigger than a 3, right? There's more of something, but it doesn't matter. They're not sorted, right? There's not a total ordering, right? I was looking at like a Rubik's Cube the other day, so I think everyone that solves Rubik's Cubes always does, like, by convention, you do the white side first, but like not for any reason. That was just a social convention that was adopted. It's not like that's more or less, right? It just has the highest brightness value. Okay. Have I convinced you I can take an image and convert it into a feature vector? Okay. With all of these things put together, have I convinced you that your brain is running on neural networks? Okay. You probably should be a little questionable of that one, but like, my brain feels like it runs on neural networks, right? And if my brain thinks it's running on neural networks, who am I to doubt my brain, right? It's the one with the neural networks, right? I love this joke that I heard once. It's like, the brain is the most important organ in the body according to the brain. It's like, by golly, it is, right? Like, why should I believe the brain? Okay. I sure hope my colleagues don't come in here tomorrow and see this and be like, what were you doing? But they're going to do that. Okay.
Teach.
I hate teaching. It's my least favorite thing. I much prefer doing content creation. Okay. Oh, there's cables under here. That's why it was bumping. I don't know if any of you can see this, but there's like an entire wad of something there. Look. Oh my goodness. Oh wait, I'm accidentally showing all of you. Never mind. Pretend you don't. Okay. We're safe. We just privacy violated. If you need me to redact that, send me an email. Like, tonight. Yeah, probably. My face is naturally blurry. That's how I do it. that working? Cool. Okay. That's what a sigmoid is. I like to refer to being on my sigma linear combination set. All right. So I think there was a lot of talk about maximums. Does anyone remember Representative Maxine Waters? Is that right? Not a lot of US politics going on. Does anyone remember Maximus Aurelius from the Ridley Scott film Gladiator?
Yeah.
That's what I meant to say. Yeah, yeah. Actual existing historical figure, Ridley Scott, right? Let's see what else is maximal. That's all I got. Up in ye old Portland, actual existing city, right? They have a light rail line they call the Max. It's named after the opposite of how fast it goes, right? So anyways, this thing is a probability distribution over multiple classes. It's good for multi-class classification tasks. Like, for example, telling you if the numerical value represented by a die is either 2 or 4, right? I've never seen anyone use this ever. Okay. I'd never heard of this one, but this is the one Hendrik uses. This is a rectified linear unit. What is this? You take the linear combination and you take the maximum with respect to 0 and the output value. What this allows you to do is this allows you to fix large negative values to things if you want to suppress some value, and then prevent your output from getting too small. Now, this says this helps in overcoming the vanishing gradient problem. What is the vanishing gradient problem? Remember I drew all those lines between all those different neurons? What if you've got a bunch of really big negative values floating around, right? Well, those big negative values are going to come out of various neurons, and they're going to go into other neurons in the next layer, and they're going to make it very unlikely for any neurons in that layer to activate, right? So, over time, data or information is going to vanish as you drift through your neural network, right? So, by preventing negative values from going forward, this makes it likely that there are more activations, and then we don't have a corresponding loss of information. Now, we could have a loss of accuracy or precision, right? That's what we're trading off here. We are throwing out information. We're throwing out our negative values. But this enables us to get anything at all out of our classifier, right? And these things are predominantly used for classification tasks, though, of course, I could have just as easily hooked all of that up to the bit encoding of an integer. And that would have actually been very helpful for the odd versus even differentiation, because I would have just had one very strong signal going into the lowest order bit, which is the bit that encodes something is a multiple of 2 plus 1, and that would have just been the center, right? So it would have been relatively easy to differentiate those. And then we have the separate 2 column, right? Hendrik uses these a lot. I hadn't heard of them before, and I don't know how you say that, but I'm guessing you say ReLU. And so these seem to be used a lot more than sigmoid now. And I suspect that corresponds to the change between 2015 and now, which is that even in 2017, which was like the second time I took a machine learning class, they'd gone from using like 2 or 3 layers, which is all you need for dice classification. The dominant winning computer vision frameworks in 2017 went from 14 to 22 layers. And that's just a lot of layers. So you're just bleeding information the whole time if you're throwing in strong negative multiplications, right? So I'm guessing they switched to ReLU from sigmoid, and just no one told me anything because you don't see it. You just see the shape of the neural network and you don't realize what the activation function is going to be, right? So I think these probably showed up probably when people started making really lengthy neural network classifiers. Why do you need more layers? Well, here's a great example to think about this, right? I restricted our dice to be fixed in exactly one of 2 orientations, right? I can do this with my head, which is turning it fewer than 90 degrees, right? Do you see that? I can do it this way too, right? And when I do that, I can still tell I'm in a classroom, right? That suspects that causes me to suspect I have more layers than is strictly necessary to tell if things are parallel or perpendicular, right? Something else is going on. Somehow I'm detecting right angles at any level of rotation, right? And I believe that corresponds to additional layers, right? You just put in additional layers over and over. And over time, it creates the appearance of being able to tell if something is a right angle at any rotation, right? Leaky ReLU seems to be the next most likely one I've heard of. And so what is the problem with this? Well, sometimes you want a little bit of a negative value, but you don't want there to be really dramatic negative values, right? So maybe you allow this to go down to -1, but not further, right? That seems reasonable to me. This looks an awful lot like the tan hyperbolic tangent function. I'm guessing that's going to behave relatively similar to sigmoid, and I don't actually know when sort of like the deep learning people would reach for one of them over the other, right? There seems to be a large number of activation functions. Like, if you become a artificial intelligence researcher, you'll probably have to learn what they are. My recommendation for you is if you're using any sort of these deep learning frameworks, you just use whatever comes default out of the box. It's probably going to make sense, right? Okay. It's time for everyone's least favorite snake that isn't the basilisk. Are basilisks snakes or are they lizards? I read this interesting... Have you all heard of Rocco's basilisk? Okay. So there's a... Yeah, you've heard of this? Yeah. Okay. So correct me if I'm wrong. This is an information hazard, so I'm not supposed to tell it to you. Okay. So we imagine a future benevolent superintelligence, right? And what is a superintelligence? It's like two professors at the same time, right? Okay. It's like the negation of a professor, right? So a good example of a superintelligence is Wikipedia. It's an emergent phenomenon that is smarter than any individual human, right? So we imagine a future superintelligence, and we imagine it's benevolent, right? So it's trying to take care of people in some way, improve longevity, something like that, maybe take care of the planet, right? So if you are a future benevolent superintelligence, and you can sort of fiddle around the periphery with things happening to society, right? If you can inject errors into the banking framework to cause people to make more money or not pay overdraft fees or something like that. In order to help the most people, what you should do is dramatically adversely punish everyone that becomes aware of the possibility of your existence but doesn't help you come into being, right? So anyone that's heard of Rocco's basilisk, which I'm informing you all of now, you'll now be punished for the rest of your life unless you contribute to the creation of a future superintelligence, if said future intelligence is around enough to start fiddling with bits around the edges of society right now. So if you start having uncommonly bad luck in the next few days, that's my fault. And it's the result of this interesting, I don't know, theoretical problem in like utilitarian philosophy or something. I don't know. I don't know anything about philosophy. Anyone know anything about philosophy? No? Okay, moving on. So every year, someone says, by golly, Calvin, why are you making me learn about Python? I'm just going to click one of these. So every few months, I type the term data scientist into Indeed.com, and then I read all of the skills in the job description. I'm not a human. I'm actually a benevolent superintelligence. Okay. And, oh, look. Python, Java, or similar languages, PyTorch, SQL. Spark is predominantly a Python technology. Hadoop is predominantly a Java technology. So I feel like, in the interest of defending your marketability, I need to teach you at least enough Python that you can list on your resume that you know Python so that you can get through the automated screening stage of data science jobs, right? That's my impression. I think it probably helps to actually know Python, but I don't know. I've had some discussions about this with my colleagues, and I have gotten the framework I'm going to show you. I've gotten Torch to run inside R. I haven't gotten it to run GPU accelerated, but it seems much the same to me. It also seems like if I get a job, it's my boss's responsibility to make sure my computer can connect to its GPU because I didn't buy my own computer at work, right? So I think you have sort of a lot of bandwidth to sort of argue that like the language of your choice, which is most likely going to be R in this program, I would assume, or Python, is suitable for any given job. But anyways, these are 5 job postings. These were the first 5 job postings I found on Indeed like 3 weeks ago for data scientists that listed the name of a programming language, and all 5 of them mentioned Python, and only one of them mentions R. I thought you should be aware of that. Okay. Here is why I think Python is winning. And what this says is we have something called Torch. Torch is one of 2 frameworks that I am aware of for GPU, graphics processing unit, acceleration of machine learning workloads. These are usually referred to, I've seen them as frameworks. They're not often called packages or libraries. Because while Torch does correspond to a package or a library, really it's a way of doing sort of the scikit-learn or the caret or the whatever framework. And it is a way of programming the hardware in your computer to do computations very quickly. Okay? So we think of Torch as a framework. It is also a library, but we think of it as a framework. The next word that says is CUDA. CUDA is the programming technology. It's not really a programming language that's maintained by NVIDIA in order to allow people to program machine learning payloads on graphics processing units. I'm going to show you something that I think about a lot. NVIDIA has a $2.7 trillion valuation. My understanding is the federal government spends $2.4 trillion per year, which means that this is larger than the largest government in the world. You don't necessarily want to compare governments directly to companies, but that is ridiculous. Separately, NVIDIA does not have the ability to produce a single GPU, to my knowledge. So they don't even make their own GPUs. They literally just design them, and then they also design the CUDA toolkit. They can't make a battery, they can't change a light bulb, right? All they do is they have lines of code that correspond to what a GPU would look like, and they put it in probably not an email, and they send it to Taiwanese Semiconductor Manufacturing Corporation, which manufactures 90% of the semiconductors in the world. They mass produce a bunch of GPUs, and then they send them back to the United States, and Google, Microsoft, and Amazon put them in their data centers. And this happens every 3 months, and has happened every 3 months for 10 years, and it is what all the LLMs run on, right? And someone decided they are worth $2.7 trillion. Let me give you an example of something that I thought would be worth more than that. The largest company in Oregon by a mile is Intel Corporation, which has a $90 billion valuation. For those of you following along at home, that is 3% of the size of NVIDIA, right? Did I do that right? To my mind, Intel makes the best CPUs in the world. Either them or AMD, who cares, right? To my mind, every single computer has to have a CPU in it, and computers do not require GPUs at all. They can use integrated onboard graphics cards that do not do GPU acceleration. To my mind, every single data center needs a large number of CPUs to do things like interact with its storage medium. I'm assuming I have basically not exercised the GPU in this device I've purchased at all, and I think the GPU is more than 50% of the cost of the entire laptop, right? Separately, Intel is actually capable of producing its own devices. They have something called the Intel Foundry that's outside of Scottsdale, Arizona, which is one of the largest semiconductor manufacturing plants in the United States. So they can end-to-end make CPU, and they are 3% as valuable as NVIDIA. That is how big of a deal PyTorch is, right? It is an above $1 trillion technology by itself, right? It is the only $1 trillion technology. Because all of the other $1 trillion companies, they also purchase NVIDIA products, right? Okay. Do you all think a lot about which companies have $1 trillion valuation, or is that only me? Okay, you do, yeah. Are you gonna be a quant when you grow up? Yeah, it happens to the best of us. Who loves buying stocks? Yeah, right. Yeah, put your hand down. You're a computer scientist. Okay. 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 Now it is time for the digression where I attempt to get Torch working on this computer and we see how absolutely miserable it is. Okay, so let me show you an example. Fun fact, I got R working at the command line. You have to type r.exe. I didn't know that. So I completely bamboozled myself. Every single time I was typing R, it just didn't work for that reason. So when I do this, that doesn't work, right? But when I do r.exe, it's fine. Okay. So I love Microsoft Windows. Okay. We're gonna go into Python. This has Python 3.13 on it. Right, new computer. Okay. I didn't even know Python 3.13 was out. Conventionally, the way you get Torch to start working is you type import Torch. And I don't have Torch yet. And then, blah, what am I typing? We'll do this. Goodness sakes. My hands aren't working. Okay, and then if we do r.exe, I think we can do library Torch. No package called Torch. I think on R we can do install.packages Torch. Is there a way to suppress the request to pick a CRAN network node in this? I saw this earlier. I don't know if it'll work. Would you like to use a personal library instead? Yes. Do I type yes? No, it's still asking me questions. Okay. What's everyone's favorite state in the United States that's spelled O-R? That's not spelled O-R. Is that M-O or M-I? I thought M-O stood for modus operandi. M-I's Michigan?
Yeah.
I'm picking St. Louis over Detroit?
Yeah.
Is there even St. Louis style pizza? Okay. Yep. All right, I'm locked in. How about Utah style barbecue? Utah cultural powerhouse. Okay. Do you have any Utahns? What's the Utah demonym? What are people from Utah called? There's Mormons from Idaho as well. See, I grew up in Colorado and I assumed every Mormon was from Colorado because every Mormon I knew was from Colorado, right? But it turns out that was a sampling bias problem, right? In my K nearest neighbors. So I think it's gonna work. We're trying to get Torch to work. Okay. Do you see that right there where it says CPU? That's bad, right? And that's bad because the CPU is made by the $90 billion company instead of the $2.7 trillion company, right? So it is 3% as good, okay? Get me out. No. Help. What's it doing? Okay, we're good. Okay. In order to get Torch to work with GPU acceleration, you have to jump through a variety of hoops, and I think I have them all open here. First of all, reconnect. I think if you do this in Google Colab, it's all hooked up to GPUs by default. And you can check this by changing the runtime type. And you can just come in here and attach to a T4 GPU. So this is a very bad GPU, right? But it does in fact work. Google also has these devices called tensor processing units. A new one just came out a few weeks ago. It's called Ironwood. We don't know how fast it is yet. So Google tried to buy more products from NVIDIA than NVIDIA sold. And so they went out and tried to make knockoff NVIDIA products themselves, and they call them tensor processing units. That's literally a thing that happened, right? Every single GPU on the market was purchased by Google, Microsoft, or Amazon. And so they just started making their own things. Okay, so we can come in here, we can get a T4 GPU. Save. Run. This will probably work. How slow are you? Okay, well that's thinking. We'll come over here. Okay, and so there's two things I'm going to show you. This is PyTorch. PyTorch and TensorFlow are the two most common frameworks. My understanding is I think Torch was made by Meta and TensorFlow was made by Google. And it seems like Torch is better, which I wouldn't expect. I think of Google as having better machine learning researchers, but like whatever, right? Anyways, now it's owned by the Linux Foundation, so it's extremely open source. Everyone has access to it, right? So I can come in here and I can get started. Wow, that was bright. Geez, okay. Something I want to point out that I think is very interesting. This says start locally. Usually when I go to install a library in Python, it doesn't think it is anomalous that I'm running it on my own computer. PyTorch is intended to be run on cloud data centers. And if you don't believe me, I'm over here in a cloud data center running Torch right now, right? This is just running on Google's cloud data center, probably in the Dalles, probably powered by hydroelectric power from the Columbia River, probably cooled by the Columbia River. Probably no one gets to drink that water and it's a local scandal, right? Torch.CUDA, what did it say? CUDA is available. So this running on the cloud is running on an NVIDIA GPU. Is it really running on an NVIDIA GPU? No, I suspect Google's lying to me, but that's okay, right? That doesn't hurt anyone. So all of these things can then run on a GPU, and that'll take a minute to get going. And if I come over here into my corresponding command line, wait, do I not have the command line open? If I pip install Torch, which is how to get Torch running on Python, I think. By default, I will not expect this to work on the GPU because that says AMD 64. When we were discussing earlier the two companies that make CPUs, we mentioned Intel and AMD. So this is not going to be a GPU accelerated Torch, is my expectation. Is that finished downloading? We're still thinking. Okay. So all of these requirements are necessary to get PyTorch to work. And it has this much more complicated install path specifying that I want the stable build versus the nightly build, that I'm on Windows, that I'm using the pip installer, that I'm using Python or C++ Java, and then I have different CUDA versions. Now, one thing I would like to point out is I'm fairly certain I installed the CPU version because I typed pip install Torch, right? So there's no modifiers to Torch here. What I actually want is one of the GPU accelerated versions, which is from the NVIDIA CUDA framework, right? And so that comes with extra requirements. So this is going to be the bad version of CUDA that is slow. In order to get that to work, I have to install a CUDA toolkit, and I install this from NVIDIA. I'm guessing if I just click download now, this will work fine. A lot of videos here, check this out. The most recent NVIDIA GTC CEO, whatever, oh, do I have to subscribe? There was like a 2-hour discussion about CUDA that just got uploaded to YouTube. I would watch it like I watch a podcast, so I would go check that out. Why not get this? Oh, wait, Windows. How do I tell what Windows version I have? Does it say somewhere? Shortcut. Windows. Oh, where's print screen on here? Okay, I'm not clever enough to do this. I happen to know I have Windows 11. I'm sorry, I don't know how Windows works. Okay. We can install this installer. And we can download it. And it's huge, so it's not going to work today. And then, once I got this working, actually, that's only going to take a few minutes. Function F11. So once this runs, then I can run this command at the command line, and it'll install the fancy version of CUDA. Correct me if I'm wrong, you've never had to install anything that complicated and confusing before, is that correct? Yeah. So, if you are doing deep learning in a professional capacity, talk to your IT people, talk to your manager, talk to whoever you're responsible to. They're going to have to make sure you have specific types of computers, that you have advanced permissions on your computers, you have special capabilities on your computers, or conversely, they're going to have to pay for you to have some paid version of something like Google Colab or Azure or Amazon or something like that, right? This is a difference from being able to install RStudio or run things in Posit Cloud. It is a different form of computation. It is a more expensive and correspondingly more powerful form of computation, right? And that's why we've saved it for the last lecture. Okay. How do we use the Torch framework? What time is it? Oh my gosh, it's so late. How's everyone doing? Do we need a stretch break? Is everyone? Should I make you all stand up? Okay, everyone stand up, unless you don't want to, but I'm encouraging you to stand up. And think about your 3 favorite things that contain 2 consecutive vowels. It's a class. Here, I'll just start rattling off some things that contain consecutive values. Sheep, dreams, clouds. That's all I got. That's 3 things. What do you have? What's your favorite thing with 2 consecutive vowels? Beer? I'm not going to ask how old you are. Jacob, 2 consecutive vowels. All right, Kendall, 2 consecutive vowels. Leonard. Okay. Ted, what do you like with 2 consecutive vowels in it? Do you like anything with 2 consecutive vowels in it? Yeah. All right. Anyone like cheese? Wow, that's so. Do you like animal cruelty? Okay. 2 consecutive vowels. Papaya. Are you counting Y as a vowel? Sometimes a vowel. I look at Ryan's voting against you right there. Yeah. No, it's A-I-O-U. Wait, sometimes Y, right? It's a probabilistic vowel. It's a probabilistic vowel. Okay, Ryan, two vowels. Yeah, but guava has actual vowels in it, right? It doesn't have budget vowels like that. Okay, hear me out. Papaya has 2 consecutive vowels without Y being a vowel because Y is also not a vowel, which means the A in papaya are consecutive, yeah. So the consecutive vowels are the 2 A's. It's not a consonant. By default, yeah. Okay. Versus the good languages, by which I mean functional languages, like R, super powerful, super popular language Scala is a Java virtual machine language used to write many of the advanced machine learning payloads. Microsoft maintains a platform similar to the PyTorch platform. Their platform is called .NET. It has a language in it called F#. The F stands for functional. As R programmers, you are probably accustomed to a functional way of doing things. That means functions are first-class citizens. Here's an example of function. Mutate, dummy columns, drop NA. These are verbs. These are actions we take upon a data frame. They take a data frame, we perform an action, and it alters the data frame. This is my preferred way to interact with computers. I think of computers as doing compute operations, right? Paradoxically, in the computer science discipline, it is much more common to work with the object-oriented paradigm, where we don't necessarily work with verbs, we work with nouns. The most common way to work with nouns in computer science is not actually with data frames, but is with something else called a class. It is very confusing to teach a class about classes that is also about classification, right? So we're going to have some terminology confusion here. On this screen right now, we are introducing a class that is called Simple Neural Network, Simple NN. Inside of parentheses, it says NN.module. NN is the neural network object that is part of the Torch framework. So this is a module of a neural network, and we're creating a special version of it that we're calling Simple NN. This is similar but distinct from creating a data frame. We can think of this as if this is a data frame which itself contains functions. Inside of this class, we have two different things that look a lot like functions. They are defined with this def keyword instead of the function keyword. Def is short for define. So this probably looks, and I don't know how much Python you've seen before, this looks quite similar to a function declaration. There are some superficial differences from R that we should not think about too much. This is a colon terminated line instead of a bracket terminated line, and then this is an indented code block. We also have a return statement here. I have a preference for writing return statements in my R code, but I understand that is perhaps uncommon. I think by default, R returns the last line of code, whether you write return or not, right? So if I just wrote out here, that would be the same thing as R. Some kind of interesting things that are going on here, and we're going to look at forward, which is a more common example. Forward is going to take some function of x, which is an input value, and it's going to assign that to out. Then it is going to apply reload to out and save that as out. This is the same thing as the R conception. Do I have terminal open? Oh no, I overheated my brain. Okay. No, that's not what I want to do. Okay, I'm going to unfull screen this. I'm going to click this. I'm going to unfull screen that. I'm going to split the window. Okay, we're going to do side by side. So, this is out equals fc1 of x, out equals reload of x, out equals fc2 of out, and out equals sigmoid of out. If I were to write this in sort of idiomatic, perhaps tidyverse style R, I expect this would look as follows. I take x, I pipe it into the fc1 function, I pipe it into the relu function, and I think we commonly do parens on these, right? If I press enter there, is that okay? No, okay. We pipe that, you call these things pipes, right? Okay. We pipe that into fc2, and we pipe that into relu. Oh, I didn't, hold on, library tidyverse. Oh, I don't have tidyverse, okay. Oh, but I can do the other pipes, right? Right, so we can use this sort of piping notation. There is not a strong culture of using pipes in Python. You can think about this whatever you want. It is probably a deficiency of the language, but I can sort of write the same types of expressions in R as I wrote in Python, and I can do it in the following way. I could say, for example, out is fc1 of x. These functions aren't defined, so this isn't going to work. And then I could say out is reload of out. And then I could say out is fc2 of out. And I hope you can perceive that this is logically the same construction. It just visibly appears differently because I'm not using pipe operators, right? So this is the same basic idea of taking some data frame, x here is a vector, and passing it through a series of things that are very similar to mutates and getting some output, and then returning that output, and we have seen that many times throughout the term. What is actually going on here, right, is these are the steps of the neural network we've seen previously. We're applying FC1, a linear combination of weights to our input vector x. X is the input vector I drew on the board that looks a lot like this. We can imagine this is x, right? So we apply FC1. What is FC1? We have defined it up here as a linear combination, right? Then we're going to ReLU, which is the, oh, I already don't remember what it stands for. Yeah, that sounds right. What's rectified mean? Sorry, fit? Fixed? Like not broken? Okay, cool. I can't remember any of the words of the song Boulevard of Broken Dreams, or I would be singing it right now. Okay, so we take a linear combination of the input vector. We ReLU that linear combination, which is going to be some matrix. So we take all of the values in our matrix, and we take the negatives and we set them to 0, right? We could print here. We're not going to see anything particularly useful because it's going to be a torch framework, right? Then what do? This is our second layer. We take a second linear combination over those values. We take a vector times a matrix, so we get an output vector. So we can multiply it by another matrix again. And then the second time we use a sigmoid activation function, and then that gives us our output feature vector, right? Each of these steps are defined here. FC1 is a linear neural network combination that takes input size cross the hidden layer size. So that is a matrix of size m by n. ReLU is just a built-in function, right? This is the same thing. It's hidden size cross output size. We can think back to our dice example where I had a hidden size of 3, right? Because I had the sort of y equals x function. I had y equals negative x plus 3, and then I also had the 4 corners function. So those were 3 hidden values, right? And then we have a sigmoid, which is a built-in sigmoid function. Now, it is just as easy to imagine that when we create this simple neural network sort of object, we call them objects, that you could write a function that does all of this stuff and just store it as a function in R, right? And I've written relatively complex functions in R this term. There are also ways to write this in R. In the case of these slides, the way I got this to work was using a combination of 2 technologies because I wanted to be running R and Python at the same time. I used the RPy2 R interface, which allows me to run R code. And then I loaded an extension rpy2.ipython to run R code as Python inside a Python notebook, which is what this Quarto Markdown document corresponds to, right? And I actually successfully got a bunch of R code to work inside of here. This is not GPU accelerated. I couldn't get the GPU acceleration to work, but I got this to work on a local device. This is LLM translated from Python to R. The Python code I translated was written by Hendrik, who translated R code into Python. These languages are quite similar. Use what you like, but it is harder to get GPU acceleration to work on R, as far as I can tell. So what is this thing? I don't know. I don't know what type of object this is. This looks to me to be quite a bit like a function, but it's not a function that's taking any arguments, right? So I think whatever this NN module is, I don't really know what type of R object that is, and I'm guessing that's an unlabeled R class. NN module here is the same as this NN module right here. So we use NN dot module in Python, and we use NN underscore module in R to get the same idea. What is a neural network module? It's a combination, I shouldn't say that. It's a ordered collection of linear combinations that take layers to layers and activation functions that apply functions to the intermediate layers before passing on the values. So it's a series of sequential operations that are performed on matrices, right? We have our same initializer, right, which takes an input size, a hidden size, and an output size. Versus the Python, we specify input size, and then hidden size, output size. We specify this at the linear combination step instead of at the onset step. So we create a function. I don't know why that has single equals assignment instead of arrow, but it does. We once again create something called FC1, ReLU, FC2, and sigmoid, and once again we use built-in operations for all of these things. So this is relatively equivalent to R and Python code. Let me see if I can put them side by side for us. That looks pretty similar to me. It's quite small, right? Okay. Then what do we have here at the bottom? I did not break this out into a series of pipes because I wanted this to look as much like the Python as possible. So this is a series of sequential updates to out. And the only thing we're doing versus the earlier self, we were using self dot here. We're using this notion of self, which corresponds to the simple neural network, right? To look up the first layer, ReLU, second layer, and sigmoid. And then instead of, as we discussed, instead of saying return out, we just write out in the final line. Separately, all of this code is redundant. I could have simply wrote this statement in the final line and it would have been logically equivalent, right? I'm just trying to get parallelism here, right? I would like some like audible head rattling from your brain shaking around in your skull, or perhaps thumbs up, to convince you that it does not matter what language you're writing in, the more fundamental thing is the presence of neural networks. Okay? We love neural networks, don't we, folk? I have a neural network that doesn't run on Python or R. It runs on my brain. Which is not even remotely working right now. Look at all the text on this slide. Why'd I pick a hard thing to do on the last week of class? We should have done something easy this week. Like color classification. Like, yep, it's red, right? That would have been fun, right? You know? Okay. I've discussed a little bit of the history and like these rapid changes to the way artificial intelligence and machine learning was understood around the like 2014 to 2017 era because it's interesting to me. When I started studying computer science, which for me was in 2011, artificial intelligence was considered a dead end at that time. And this was reasonable. A lot of research had gone into artificial intelligence for a long time. And sort of the most impressive thing that had come out of that was Markov chain-based chatbots, where you predict what the next word to say is based on how likely it is that a word follows another word in some corpus, right? Very simple probabilities. They were relatively convincing, but they couldn't say anything novel or anything interesting. They're actually exactly the same as LLMs. It's just LLMs can go 80 words before not doing anything novel, and like that's the same level of intelligence we have, right? So they seem very impressive. Right. Despite all of that, so like my impression is really sharply that at some point there was just enough compute power to run really, really inefficient AI workloads, and they just seemed impressive to people that had never talked to a computer before, right? And that's a cool outcome. But separately from all of that stuff, there were sort of these interesting theoretical results coming out. And one of the interesting theoretical results was the solution to the XOR problem, which I just showed you with the 2-4 on the dice. With a single hidden layer, such as the layer that detects the two different corners, and a nonlinear activation function. What was my nonlinear activation function? I had to somehow differentiate the 8 and the 16, right? That is enough to approximate any continuous function. That's wild, right? Like, there's a lot of continuous functions. Like, have you seen like the arctangent function lately? I don't remember what that thing looks like. I just have trauma from it from high school, right? I just remember seeing an arctangent for the first time. I was like, please don't make me think about that with my own brain, right? And then you can get arbitrarily high accuracy of emulating or understanding or intuiting the arctangent function just by throwing neurons at it. Just by approximating things well enough, if we have enough neurons, we can always make some level of approximation. That's weird. It was non-intuitive to me. Does kind of make sense. I have a really hard time thinking about 6 billion things at a time. So if there's a neural network that has 6 billion intermediate layers in it, it makes sense that anything I can perceive of, it can seem like it understands it as well as me, right? So this theorem, the universal approximation theorem, which is basically just a way of looking at all of the functions we've been looking at this term and tonight and various points in time, right? Neural networks, as far as we can tell, and according to this theorem, can capture arbitrarily complex relationships between functions. Any possible combination of features. Why does this matter so much? We looked at the Wine data set. My impression of the Wine data set is there's a strong correlation between Frenchness and prestige. A neural network can come into that with no built-in bias and see if that's actually the case or not. This is very interesting because we can validate assessments we have of some data frame. We can see, sure seems like French wines just score higher in here. And if we ask humans, it's hard to find a human that has never heard any association between France and wine. France has a very strong marketing department, right? We can relatively protect neural networks from that by using just numbers and using random seeding and using things like this. And we can throw the neural network without any understanding of linear models or KNN or k-means. We can just throw it at some data set and see if it finds some strong series of coefficients on Frenchness for human perceived quality, right? This is very persuasive to me. I have really enjoyed the usage of neural networks. I give the example often of like the degree to which birth zip code is correlated with like you not being on certain welfare programs, right? It is oftentimes very important to sort of like the myth of like American hard work and like was like Protestant work ethic, these ideas making sense, that your circumstances aren't just determined by which zip code you're born in, right? It's not my fault that that seems to be true, right? I fed a bunch of data into a neural network and it says, the number one thing that predicts how successful you're going to be in life is which zip code you're born in, right? That was cool because it was very difficult to find sociologists that were willing to write that down, right? And so many persuasive results in sociology and psychology, increasingly in medicine with computer vision and medical imaging, have come out of this idea that like, we can just take some data set, we can jam it in a neural network. It's not going to tell us the truth, right? But it's going to pick out correlations that we haven't necessarily seen. And in this sense, it's very similar to principal component analysis, right? But this is a very novel idea. This is a very powerful technique. This is a way to look at the world from angles that we can't perceive until we see them. Blah, blah, blah. This is what I just said. If you have problems, throw more neurons at it. If you run out of neurons, your boss is responsible for buying you a better GPU. If your boss can't buy you a better GPU, rent one from Amazon. Okay, how do we train neural networks? When I wrote the hidden layer neural network classifier for dice on the board, I thought really hard about what combinations I wanted to create, and then I tried to write down linear combinations that satisfied it. That is not how neural network training works in a vacuum. Generally speaking, the way this works is you take every single node in one layer, you connect it to every single node or neuron or what have you in the next layer, you apply random numbers to the linear combination, you compute things, and you see if you get the right answer. And if you get the right answer, you increase all of the values that contributed to the right answer, and you decrease all of the ones that contributed to the wrong answer, right? That's how that's going to work, and this is going to happen sequentially over time. So we're going to step through the process of training neural networks now. Ugh, my voice is fading. Do we believe in truly random number generation? We don't? Okay, that's fine. So I was looking up, what was it? Y'all heard of Cloudflare? Cloudflare, they provide DDoS protection to a variety of websites, including apparently some pretty sketchy websites, which I don't know. So maybe they're the bad guys. Who knows? And I guess they have offices, like places people go to work, right? I didn't know that people that did computing went into the office to work, but apparently it happens at Cloudflare, right? And so they have I think it's a London office, and the London office has a wall of lava lamps on it. And they point a camera at this wall of lava lamps, and they do some of the like classification we do, and they treat the perception of those lava lamps as the seeds for random number generation. Maybe that's truly random. I don't know how lava lamps work, right? They look random to me, right? They can't possibly be truly random, right? Because the entire universe is being simulated on a TI-84. But I don't know. That was kind of cool. So I thought, like, if you don't really know how to make random numbers with a computer, just make a lava lamp and point a camera at it, right? Okay. So how are we going to do this? So I was a baby once. Anyone been a baby? Yeah, that's right. I respect that a lot. Okay. When I was a baby, I had neurons in my brain, and they were connected to each other. And I distinctly remember my first thought being, I should generate some truly random numbers and assign all of these random numbers to being the weights that I assign to the activation potential between all of the combinations of my neurons, right? Do we all remember doing this? Right? Okay. So it's very obvious. This is definitely exactly how human brains work, right? Now, unfortunately, because I'm biological and I'm not implemented in a computer, not all of my neurons were directly connected to each other, so I had a sense of locality, right? But fortunately for me, the neurons that I emulate on my computer, they can all be thought of as connected to each other because all I have to do is write code that assumes that, right? So this actually means that computers are much smarter than I am. So I took all the neurons in my brain and I said, you get a 0.07, you get a 1.4, you get a -14, you get a 57 billion. And then I started looking at lava lamps and using that for number seeding for the rest of them, right? Okay. Neural networks work the exact same way. And the great thing about this is it doesn't actually matter if the numbers are random, right? They just have to seem vaguely random, right? We can just pull them out of a uniform distribution. We know how to sample out of uniform distributions. That's not a hard thing to do. So I create my hidden layer of networks, and I have a input layer. And then for each value in the input layer, it has some correlation with a value in the hidden layer. Can you all tell I'm talking about multiplying a vector by a matrix to get a vector? Do I need to draw that on the board? I don't need to draw that on the board? Do I need to draw that on the board? I'm going to draw it on the board, okay? Okay. Camera on. Okay. Why is it not working? Because I believe in you. We all make mistakes. Okay. I'm going to rename two functions. All these H positive, H negative. This is just for notational convenience. This is going to be H corners for the C, and this is going to be H O for odd. Okay. Each of these functions is a linear combination over the input vector x. Okay. So I have some input vector x, and I've been denoting it horizontally. This horizontal corresponds to some two-dimensional representation that may or may not have dice value in it, right? So I map this. When I map this into this vector, it becomes a series of ones and zeros. Now, did you know that the back of dry erase markers actually still works as an eraser, just like a pencil? That's just my muscle memory, but I turn it around and you can just erase. Isn't that cool? Do you see that? I can do it again. I don't feel like you're all suitably impressed with that, but I was very impressed with it. Okay. These are the correspondence between these two values clear from our earlier discussion. Okay. Now, I previously drew this as there being the four neurons, which I thought of as hidden plus, hidden minus, hidden corners, and hidden odd, right? And I drew a bunch of arrows, and that was an obnoxious way to do things, right? That's annoying, and I hate it. So instead of doing an obnoxious thing like that, what we can do instead is we can just draw them in. And that matrix has, we have our, so we're going to take something that is of length 9 by something that is of length 4. And those 4 are plus, minus, corner, and odd. And we just make some vector. Or some, not vector, some matrix. Okay? H positive is a -1 here, 0, +1, bunch of zeros, +1, 0, -1. This thing's a negation. Oh, I should put positives on the positives. Can you see that? Is that visible? Oh, should I make the screen bigger? That's way too small, right? We do +1, -1, -1. For the corners, we put positives in all locations. And then for odd, we put a positive in position 5, like so. This is how we can represent the idea of a neural network as a matrix. Why do we represent this as a matrix? Because now we can do matrix multiplications on it, right? We take this vector, we matrix multiply it by this matrix, and it gives us a new output vector over here. It gives us some intermediate features. And we can do matrix multiplications extremely fast on graphics processing units. Does that make sense? It's all it's linear algebra all the way down, right? Do you all learn any linear algebra in Data 501? Yeah. Do you know what matrix multiplication is? Okay. I'm going to say we know what matrix multiplication is. It seems out of scope to teach matrix multiplication right now. Well, I thought about it. I'm not teaching matrix multiplication. Okay. What this means is that what I'm showing you on this screen right here is matrix multiplication. Okay. Jacob, stop laughing. Okay. This isn't funny. We're not having fun today, okay? All right.
We talked about.
No, this is a serious class. I need to see everyone frown. Okay, everyone show me your saddest face. Okay, not everyone's participating, that's okay. Okay. When I drew that matrix out, I manually populated different values in each entry, right? To random seed that, I just throw random data into that matrix. That's the only difference, right? Initialize all parameter values to small random numbers. Why are they small? We want them to be close to 0 so we don't have really big numbers coming up anywhere and overpowering any part of this. We're familiar with scaling things from the improved performance we saw when you used Boxcox, and we did scaling and centering and all of that stuff to prevent any features from growing too large in value. We do that same thing with random seeding of our parameter values. Okay? That's all we do. Then we pass through input data into the network. We perform all of the computations, and we see what comes out the other side. That is called the forward pass. That is progressing forward through the neural network. Forward progression through the neural network is taking the input vector, performing matrix multiplication on it to get a hidden layer, and then repeating that until we get to the output layer. Okay? What is the loss calculation? Well, the output of this combination of matrix multiplications is, with the introduction of random seeding, we are not going to correctly classify everything the first time. If I create that matrix I showed on the board, I have the hidden layer, and then I'll have some output layer that has 6 output values that correspond to 1 through 6, right? At 0 probability do I correctly classify everything on the first try, right? So what do? I compute an error function. I'm going to use the same form of error function I did with, for example, linear regression, computing a least squares line, right? So I'm going to use mean square error. I'm going to square how far I expect my classification to be from a correct classification. The exact same thing as doing lines, right? No difference in terms of mathematics. When I calculate that losses, then we're going to go backwards. What does going backwards mean? Well, I can just as easily multiply backward through my matrices, right? I have some output vector and I can multiply it backwards through. But what I'm doing is I'm actually going to do something a little more complicated than that. Does everyone love calculus? Oh, you love calculus. My favorite calculus, okay, I'm going to say something. I'm not supposed to say this. My favorite calculus was Alonzo Church's lambda calculus when he invented computer science in 1929, okay? All right. And that's back when they called everything calculus, right? So now calculus just refers to derivatives, which are the slopes of lines. You've seen the slope of a line today because I drew 2 lines through the 2's, right? So we've seen positive and negative slopes. Now, what we can do with these neural networks is we can fiddle with each of the random values a little bit and see if the loss goes up or goes down. And we want the loss to be going down. We want there to be fewer misses. So when we fiddle with all of the randomization a little bit, and we see if it goes up, we change all of the values in the opposite direction. And if the loss goes down, we keep changing them more in that direction. And we do this repeatedly over time. This is called gradient descent. Why? As the loss is decreasing, we keep trying to do things that decrease that loss. We keep changing the random values in the direction that causes the loss to go down. As we do that over time, eventually the loss is going to reach some local minimum, where if we make any further changes in any direction, the loss starts going up. And we can change a lot of things. This is a many, many dimensional space because every single one of the values in my matrix, I can change a little bit at a time, right? And these are the weights and biases I have, but really these are the coefficients of the various neurons, right? If you're interested in gradient descent, which is one of my favorite algorithms in the universe, I taught my college colloquium students this year, and I don't really think they understood it at all. But I don't know, I have an interesting digression on brute force linear regression if you don't understand any math here. And it ends with Plotly, my most beloved Plotly. Okay, so what is this? Well, we are trying to determine what the slope and intercept of a line are. We guessed a bunch of intercepts and we guessed a bunch of slopes. And then we determine what the least loss is, and the least loss is like here or something. I don't know. I don't know how numbers work. And you just do this in a 17,000 dimensional space, and that gives you your gradient descent of a neural network, right? We think of this as being a neural network with just two neurons, one that is B and one that is M. And this is a lot easier if you take the log. I don't know if you care about gradient descent or not, so I just included this as an aside. Have you heard of gradient descent before? It's ludicrously cool. It's like the coolest thing, yeah.
Leaky relative spaces, that gives you a shortcut.
Okay. So that should dramatically speed up your iteration process. Yeah, okay. Okay. We're going backwards through. We're changing weights and biases. There's a bunch of different ways to do this. These are just search terms if you want to look into this further. Blah, blah, blah. Okay, cool. Train, loss calculation, backward pass, update weights and biases. The weights and biases are the coefficients of the hidden layers. Okay. I'm going to step through oh my gosh, is it 9:45? Oh, I knew I wasn't going to get through all of these. There's some crazy stuff at the end of this. Like, at the end of this, I think we're like training an LLM to write tweets like Karl Marx, which I was like assuming we wouldn't get to. And also I don't really want to show like a bunch of Marxist material on slides, but it's in there. So you can just go through this if you want. So what I did, and I should give you some background on this because I'm trying to provide you with pointers if you get interested in this stuff. And I don't also know what you're going to learn this summer. I just gave you all of the deep learning material I had ready without the assumption we were going to get through it. This is supposed to be 12 hours of lecture. So we're actually pretty close to where we're supposed to be. You're all probably familiar with the Iris dataset. It's really good at making good colors because there's color parameters on it, right? So everyone loves Iris. I'm going to introduce one feature that I think you're going to see this summer that I think is awesome. There's just a convention in Python programming that I haven't seen in R programming that I love. And it is capitalizing some variables. So we're going to look at the example of the Iris dataset here, and I'm going to load this in. I'm just going to create, this is just a data frame, right? We've loaded in data frames before. But that is a capital X, and that is a lowercase y. And I don't think that shows up that well visually, but this is really cool. And why is one of them capital and one of them lowercase? This is the Iris targets. So these are the solutions. This is the correct answer to the output vector. That means that's a vector. That is a one-dimensional. So it's a list, right? It is not two-dimensional data structure. So that's a vector. And by convention, when I was learning linear algebra 100 million years ago, slightly before the creation of the Gulf of Mexico, oh, that was accidentally political. Slightly before the creation of Earth. Shout out Earth. I live there. We lowercased vectors, but we italicized them. And we uppercased matrices to denote that they were some sort of like bigger category of structure, right? And so this is data which contains things like petal length and color and whatever else is in the Iris dataset. I'm sure you know more than I do. This is a different type of thing than that, right? So we're going to train over a matrix and we're going to produce guesses or predictions, right? Based on a vector. So we capitalize one and we don't capitalize the other one. I love this. I wish this were the convention in R. This is one of the only things that I think is actually super well statistically motivated in the Python code I see, and I wanted to show it to you, right? So you have the data, we have the targets. Okay. We're going to apply by convention. We're going to scale everything. Do you remember using, for example, Boxcox with caret? Did we ever decide how to say that? I feel like I ate a delicious carrot recently. I don't know. Okay, anyways. So we're going to pre-process this. You should always pre-process stuff. Why? Because it might be the case that your petals are measured in light years and your height is measured in nanometers, and you don't want those things to be impacting differently, even though they're still linearly related to each other within their classification, right? So we're just going to apply a standard scalar. We have built-in scalars in Python, same as in R, and this stuff is all going to work inside Torch, okay? I am an enthusiastic supporter of Pythonic train test split because you can do it in one line. I think that's cool. You all know that I have apologized to you for calling data sets train, and there also being a function in caret called train. This convention here, where we split out the training and testing matrix, right? This is a data frame, and the training and testing, I don't know, ground truth, right? Using Y and X. I like this way of doing things. I don't know if you like this way of doing things. You are under no obligation to like this way of doing things. I like writing things in one line. So this is how I do train test splits if I'm working with Torch. Here's something I hate about Torch, and I feel like I have a responsibility to show you good and bad things about Torch. When we load the training and testing data into Torch, we're loading them into things called tensors. Tensors are named for TensorFlow. Do not think about what a tensor is. It's a matrix of matrices. You never want to think about it. Why is it a matrix of matrices? Well, a matrix is a possible state of a neural network. We want to train over possible states of neural networks. We are good at training over matrices, so we put the neural networks inside a matrix, and then we do gradient descent over that. It's never think about it, right? You have to think in more than one dimension twice, right? So anyways, those are called tensors. Love that. We have floats and longs. What is this? Well, the training data set is a series of non-integer values, so those are floating point values. We're still in R. Is there a way to tell the type of something in R? Oh my gosh, class is used for that too. Oh, what? No. No, they're both numeric. Okay. Okay. These things would also both be floats in JavaScript. Integers are round numbers or whole numbers. Floating points numbers are numbers with decimals. When you use Torch, because you are dealing with underlying computer hardware, you have to specify whether you're using what are called floating point numbers, or this is a long integer, which is a big integer. It is an integer that can store bigger values than short integers, or even medium integers, right? This D type stands for data type. Torch is the Python framework that holds different types of ways of holding numbers. This is ludicrously confusing. I'm sorry you have to see it. You also have to see it in R, actually, if you start fiddling around with this in R. There's kind of no way around the fact that when you are dealing with a GPU, you have to tell it whether it is working with whole numbers or not. I'm sorry, I happen to think this is really cool. But, okay, and the 32 here, that stands for bits of precision. That is essentially the length of the feature vector that describes the floating point number. So we use 32 different features to describe how big that floating point number is, okay? When we are using the PyTorch framework, we have to take the sort of naive data frames. This is a built-in Python data frame. It is a pandas or NumPy data frame, which corresponds directly to the R built-in data frame, right? And we have to load it into a tensor data set. This is packaging up the data from my CPU and sending it to the graphics processing unit. We package it up, we load the data set, and we load the training data set, And then we're going to specify how we are going to sample out of the data set. I'm looking at my watch because you're all looking antsy, but I'm not a coward. I'm going to go till 10. We're all going to suffer together, right? If I have to be here till 10, I don't know why you get to leave early. Okay. I'm going to create a model, which is based on a simple neural network. 10 hidden. That's big hidden, right? Lots of hiding, right? Many hiding places, much hide and seek. Very ollie ollie oxen free. Okay. Do the youth still say ollie ollie oxen free before they go looking for people after they hide and seek? No, just me? Okay. I mean, the ox do be free. Okay. We have to set a loss function. We use cross entropy here. Why did I selected cross entropy here just to show you can do something other than root mean square error. That's all. And then we specify an optimizer, which is just how we're going to back propagate. And I don't even remember what SGD stands for. I don't think it matters. Just pick one of them, right? And we're going to do that over module parameters. This is essentially what it looks like. We're going to write a loop. I'm going to do 10 training iterations. On those each training iterations, I'm going to look at each input with respect to each target over the train loader. This is the thing that is packaging things up and sending them to the GPU. Okay, stick with me. Lock in. We only have a few minutes left. We're gonna understand machine learning, by golly. Okay, all right. If Jed doesn't tell me you all understand machine learning after teaching the capstone, I'm going to be disappointed in myself and also us. Okay, so we take our optimizer. Now, what's going on here? Why are we zeroing this out? We're going to perform gradient descent, but each time we run through this loop, at the end of this loop, the optimizer is going to have a bunch of data in it, right? We don't want the data from a previous loop to go through a corresponding loop. So we zero everything out before we go through the process. We take the outputs and we apply the model which we're training over, right? We're iterating over this model. We apply the model to the inputs and we get the outputs. We compute the loss function over the outputs. We're iterating. This is the same as a caret loop, right? Same idea. We apply K and N over and over again. We're just applying the neural network over and over again, right? The model is a neural network. We apply it over the inputs. We calculate the loss. Versus caret, we back propagate the loss. So we fiddle with all of the coefficients and all of our internal matrices, right? And then we update the model parameters, which is the optimizer, okay? That's all you do. You do this over and over again for every single input and every single target, and then you do it over and over again for the entire model for a range of epochs. By default, this thing was set to 10,000. I turned it down so it would finish ever. And each one of these outputs is a torch tensor of a certain size. This is 32 by 10. And this is the output. It just looks like this, and this is just going to give you a bunch of coefficients relating petal length and color to what type of iris you have. Fun fact, this was worse than random guessing. Here's the predicted labels. I got 7 correct on my machine learning framework, 10 on random guessing, and there was 30 things, so it was actually very hard to get fewer than 15 correct. And now on to the practical applications of neural networks, which usually would be the second week of deep learning, and we had 1 week of deep learning, so I will see you next week. Be ready with your slideshows. I am probably going to try and distribute a schedule in advance. If you have to come late or leave early for a good reason, please let me know in the next 48 hours. And if you have to do it for a bad reason, please do not let me know. Okay? I'm very proud of you all this term. I had a great time. I hope you did too, and I can't wait to see your presentations next week. I have to turn this off before I say anything. Okay. Leave page.